Good evening, everyone. Still, people are joining. So, though it's not 6, but let's wait for maybe 1, 2 minutes more before we start. It's still 1 minute to 6. No, someone has written me that I'm not hearing anything, but that's not because of any system error. That's because none of us are speaking. We're just waiting for others to join. So, if you can hear me now, it's your system is okay, and our system is also okay. So, it's time to start the fourth day of International and Young Quantum Scientist Meet. So, as it was in the last 3 days, every day is divided into 2 sessions. And in the first session, Dr. Amit Bharma will chair it. Dr. Bharma works on both quantum optics and quantum information, and he is a faculty at JP Institute of Information Technology. So, over to Dr. Bharma for presiding over the first session.
Good evening, everyone. Today's first session is on quantum optics, and our first speaker is Dr. Kishore from Norway. And his title of talk is Engineering Non-Classical Light for Quantum Technology from Gaussian Foundations. So, Kishore, can you start?
Yeah, hello. Good evening, sir.
Good evening.
Yeah.
It's
So,
already
thank you.
already hot in India, means, and then we can see the difference looking at you.
Yeah, but we have a sunny day after maybe a week now. Finally, we have a sunny day.
Okay, so just please continue with your talk.
Yeah. So, first of all, I would like to thank Professor Pathak and Sandeep and Shivani, everyone, for organizing the conference once more and giving me this opportunity. I would like to share my screen. So
Still,
can
it's
you
not
see my
visible, but
screen?
but now it is visible.
Yeah, I make full screen. Is it visible?
Yes, yes. Please continue.
Yeah. So I try to keep a small amount of information so that I'm looking for more questions. And if you have too many questions, then please feel free to write to me as well. And yeah, so today I'm going to talk briefly about our recent experiments and some theory and all. And I'm giving more like an overview of this. Um, so I'm going to talk about both Gaussian and non-Gaussian states. So I tried to make this title which included both of them, both Gaussian and non-Gaussian. So in general, we are going to talk about quantum technology and everything. So in classical, in quantum optics, generally it is very easy or relatively mathematically easy to identify the states which are useful for quantum technology. So these states are identified as from the Glauber-Sudarshan P function. And for example, which is given in this equation, I hope you can see my mouse moving here. And where if given a density matrix or a state rho, if we expand that in coherent state basis, and if this P function is I request everyone to.
I'm going to mute everyone. Then Kishore, please unmute yourself.
I don't.
Kishore, now unmute yourself.
Yeah, so I think I'm audible now, right?
Yes, yes.
So for example, if we can easily see in this, alpha is a coherent state. So if we think a coherent state beta, and if we are writing this, then it will be a delta function. So for states like Fock states, it will be singular than delta function because it will have derivatives of the delta function, and the same way like squeeze state and entangled state will have negative p function and all. So I'm not going to go in all these detail because this is just textbook material. But these are all examples of single photon state, squeeze state, and entangled state. So as I already told you that coherent state, which is kind of a boundary, on one side we have classical states like thermal states and all. On the other side, we have quantum non-classical states, which are useful for quantum technology. So, so we know I have already shown you that it is for delta B function is delta function for coherent state. So it is not measurable or easily measurable in most of the cases. So we rather use Wigner function, which is a Gaussified or Gaussian smooth version, where we can see this is a P function. We multiply it with a Gaussian, and that's why it is, for example, for coherent state, it is this Gaussian peak, and which is at the value in position momentum quadrature plotted here, where we see that the peak is at the value of real and imaginary part of alpha. So so here I am showing 3 examples of Gaussian states and 1 non-Gaussian state. So in these 3 cases, coherent state, squeezed vacuum, and 2-mode squeezed vacuum, which is an example of entangled state. So in these 3 cases, we can see that these are 3 operations: displacement operation, single mode squeezing, and 2-mode squeezing, which generates these states from vacuum. So and in all these 3 unitary operations, we can see that these are like quadratic in form, like with strong pumping. So we can easily visualize them in terms of the Hamiltonians, which because unitary is exponential of Hamiltonian in this scenario, then so Hamiltonian only contains the quadratic terms. And that's why in general, if we are starting with Gaussian states and if our Hamiltonian only has up to quadratic terms, especially in terms of these with strong form conditions, we end up with Gaussian states and all. But for non-Gaussian states, for example, single photon state, where we can see here that negative Wigner function, we don't have any such unitary to generate this state and all. So this is all you already may be already aware of this. So we can see that for Gaussian states, because all these set that I'm showing here is pure state. So Gaussian states have positive Wigner function, and the non-Gaussian state has negative Wigner function, but which is not necessarily general for mixed states. So how we use all these states depends what you want to do. For example, we want to do communication, cryptography, computing, or phase sensing, or all these other quantum technological advantages in sensing and metrology, etc. So we use different kinds of states, which I have already introduced: single photon, or entangled states, or squeeze states. So you may already be aware, so I will just skip this part then. So I'll just introduce, so I have already shown you this, but I will show you how it is helpful in our cases. For example, if we are dealing with the Gaussian states or quadratic Hamiltonians. So for example, in Heisenberg approach, when we are writing the Heisenberg-Langevin equation, for example, for given Hamiltonian, if we are writing the set of equations for annihilation and creation operators associated with all the field operators in the Hamiltonian. So we can write them in a matrix form. So this is just, I want to give an overview that we already know some things generally, that if we are writing like this, then we can in general diagonalize this matrix M2, which is just diagonalization of any matrix that, but then we can write it in a transformed basis. We are thinking that we are not talking about the same operators, A dagger that we were initially talking about. Now we are talking about B dagger, which are now in the transformed basis, where this M, which is more dynamical matrix, is now diagonal. And in principle, we can, because this is now diagonal, so we can just write directly exponential to it, and then we can go back to the original by transforming them. But this is just the introduction that we already use, like most of you may have already used. But what I want to base on that is, so what we have used in these two papers, we have used this formalism to show that in case of Gaussian states and Gaussian like quadratic Hamiltonians, we can write using these two B and B dagger, which is now where the dynamical matrix is diagonal. We can write all the higher order moments and their dynamical equation. We can write in terms of first two moments, like B dagger, and all these terms. And all the frequencies, eigenfrequencies, which are appearing there are actually combinations of the first order, which were appearing in the first order. So there is no new frequency appearing in the higher order term. And also eigenvectors can be reconstructed using just tensor product space. So what we found in that scenario, in general, higher order moment space can be reconstructed by just obtaining the lower order equations. And then we were interested in looking for degeneracy of eigenvalues and eigenvectors, but I'm not going to go into detail. But I want to show that how it makes our life simpler in case of Gaussian. But that simplicity is not always desirable. For example, this simplicity restricts us to get infinite possibility or advantage that we can attain in quantum domain. For example, we can't have entanglement distillation without using a Gaussian non-Gaussian operation. So for example, here I'm giving an example of where photon subtraction is used. So here in the first block, in the state preparation, you see entanglement is generated. And then in the second block, if you just forget about the second block at the moment, in the third block, we are doing double homodyne detection, and then which is balanced homodyne detection, and where this local oscillator, by varying the phase, you are choosing the phase, the position or momentum quadrature or any other combination of them. And then we have a BH difference of the current coming from two balanced homodyne detections, which gives us the correlation between two quadratures. And so if we want to have the entanglement distillation, so if we take a small part of it, which is subtracted by using a beam splitter, and then we detect here, if we would have done balanced homodyne detection there, then we could not have distill the entanglement or improved entanglement further. But we have to do a photon number measurement, or with on-off detectors, post-selecting on non-zero detection. So that is required for entanglement distillation. The same thing with computation, key distribution, error correction. For improvement, we require non-Gaussian operations. So one example of entanglement generation is, which we usually use, and is the generation of Gaussian states, is spontaneous parametric down conversion. Here I'm giving an example of type 1 generation, where we see that pump photon annihilates to generate a signal and a idler photon pair. And with the energy conservation, we know that if there is a signal photon, then there is a corresponding idler photon. And momentum conservation gives you that if you have a photon here, then we have its pair photon diagonally opposite to it. And so we can write this two-mode squeezed vacuum entangled state in this form, where we have n signal and n idler photons, and the photon number distribution is governed by thermal distribution. And so we can see here easily that why it is an entangled state, because you can't write a pure state independently for idler. But if we post-select the number of photons in signal, we write a pure Fock state for idler. In the same way, if we just trace out signal, we write a thermal state for idler. So in principle, we have three kinds of states, which kind of gives one state of each type. That's why we use this kind of state. So this is again the same
Kishore?
on the first. Yes.
5 more minutes.
Yes. So I will try to summarize. So this is similar figure that we have just seen, that where we were using entanglement distillation using photon subtraction. So here just we have replaced it with a twin beam. And similarly photon addition, where we are adding photons by post-selecting on this. So what I want to show, that we need 4 detectors in photon number resolving detectors for subtraction and addition. So in this experiment, which I have, if I remember correctly, I also shown the last time, we used one ICCD camera, and we use 4 detection areas to mimic the photon number resolving detections, and the same way for subtraction and addition. But I have already shown this last time, so I will not go into detail of this, but I will summarize that, and that theoretically this is what we expect from photon subtraction and addition. But what we get experimentally for 1/4 detection efficiency is something like this. So we have to use some reconstruction methods to reconstruct these, and then we see some similarity with this case. But there was there were a lot of errors, because the post-selected cases are probabilistic, and the events were less probable, and that's why we designed some other experiment that I will show you further. So what I wanted to show you, that these states were non-classical, because I wanted to show you again in terms of this, like this is a P function kind of, but we have now 4 quantities. So we are showing the marginals, and where we can see the negative region in the blue color, and the blue color is signature of non-classicality. So these states are useful for cryptography and spectroscopy, etc. So this is what I wanted to show. We increase the number of repetitions. So now we have these cases highly probable, and so the probability is still low, but the events are repeated more often, and then we reduce the experimental errors. And now we have done it for very intense beams, and we could subtract up to 20 photons, and we could add up to 20 photons. And so this is how the experiment was done, because it was done with the weak twin beams and with on-off detectors, and then we concatenate data. I will skip the details, but I'll just show that we have also used then that further study that we found some quantities which can be which can be conserved in a linear optical multiport. And so I'll skip summary. You can read, and thank you. And I'm looking forward for some questions. I hope I'm not doing that on the screen. Am I audible?
Yes, and now I guess now it can be open for question.
Okay, questions, please. You may type in the chat box or you can unmute
And
yourself.
unmute and also ask.
Yes.
So there is a Kishore, you can see that there is a question from Miss Abul in chat room.
Can this framework prescribe entangled Gaussian states? Yeah, so actually this is what I was giving an example of that. So for example, if you see here, this is two-mode squeezed vacuum, so which is an entangled state. So now I am showing the position quadratures for two beams, but in principle, if you plot for position and momentum quadrature only for one beam, you would have got thermal state, so which would have looked much similar to coherent state and much broader like that. So more like a Gaussian, broader Gaussian. But because now we are seeing correlation, so that's why it is squeezed. And if when you are asking about the Langevin approach, what I am saying, it depends on the Hamiltonian. For example, what we have done was for quadratic Hamiltonians with two-mode squeezing as well as single-mode beam splitter interactions and all. And yes, it will work in general as long as we have only quadratic terms. For example, like this.
Okay.
Is it
Kishore,
clear
next
or-
question. Next question
Hello?
is related to the Langevin approach.
Yeah, so this is what I was saying. For example, this Hamiltonian, when you will write this Hamiltonian corresponding to two-mode squeezing. So I was giving you an example what we did. So all these three terms, for example, the Hamiltonian corresponding to the displacement operator, it will be beam splitter interaction, and this one will be more like with a strong pumping. It will be a square, more like a second harmonic generation or subharmonic generation, and this like two parametric down conversion. All these terms can be there, and once you write this, then in the Langevin equations, this will be in general Gaussian entangled states. So as long as you have a beam splitter and a single mode squeezing or two mode squeezing, you will have entangled state, Gaussian entangled states.
Okay, thanks. Thanks, Kishore, for a nice talk.
Hello, sir. As you know, this method, parametric down conversion methods, rely on probabilistic approach. Means if we make 100 photons and it will only generate 50 to 20 photon entangle. So this is probabilistic method, and you know, nano quantum dots generates in on demand quantum states, entangled states. So what is the benefits of these methods?
Yes, so what you are mentioning about the entanglement generation with this, so if in photon numbers you will have ideal pairing here. For example, I will then show you this experiment. So this beam is coming, and now we have a PBS to regulate the intensity of the beam falling on the BBO crystal. And now we have this cone, which I am just showing, but type 1 cone. And so we are taking the signal which is directly falling on the ICCD and idler, which is from this reflected from highly reflective mirror. And now we have this signal and idler as the two parallel beams. And if we will count the photon numbers here, if we would have used the ideal photon number resolving detector, then we have R parameter, which is actual which is the variance of photon number difference, which is 0. And ideally, that means there are equal number of photons in signal and idler. So when you are saying in terms of entanglement. So it doesn't matter how many pairs are produced. So what I will show you is this. So it doesn't matter how many n's are there, but it will be n comma n. So it will be always equal number of photons in signal and idler. And when, because we are using like the real detectors with detection efficiencies close to 1/4, and in other experiment it was 1/3. And in those cases, we are measuring 1 out of 4 or 1 out of 3 photons, and therefore we lose the pairing in that. And but we can always reconstruct the field before detection if we use suitable reconstruction mechanisms. And when you are talking about the quantum dots, yes, quantum dots are good sources for single photon generation. And in this case, the single photon generated in quantum dots are better, but sometimes the time the way we do it, we are interested in sub-Bosonian beams with higher average photon numbers, and quantum dots are sometimes not that efficient for that. So what we required, for example, was 5 photons in one pulse, and quantum dots are not efficient for that. But like there are advantages of quantum dots using them, and I haven't had any experiment with that, so I can't comment exactly one-to-one on that from my experience.
Okay. Thanks, Kishore. The
Thank you.
other participants may ask question directly to Kishore. The email ID was available, and now it is time to move for the next talk. And is there Bivas Malik from SN Bose, Kolkata? Kindly share your slides, Bivas Malik.
Yes. Am I audible?
Yes, you are
Yes,
audible. Share
audible.
share your
We can see
slides.
you also.
Okay. Can you able to see my screen?
Yes, but make it full screen.
Is it fine now?
Perfect. Please
Yes.
start your talk.
Okay. Thank you to the organizer for giving me the opportunity to present our work here. So my name is Bivas Malik, and I am a senior research fellow at SN Bose National Center for Basic Science, Kolkata. So today the title of my talk is Detecting Genuine Multipetite Entanglement Using Moments of Positive Maps. So this talk is actually based on our recent work, which has been published in Physical Review A. And this work has been done along with my colleagues, Soheli from SN Bose, Sahil from SN Bose, and Anandada, who is an assistant professor in IIT Goa, and my supervisor, Professor Archanis Mujumdar. Okay, thank you. So this is a rough outline of my talk. That is, firstly, I go through the motivation part. That is, that why we need to detect entanglement, and after that, I will move towards the bipartite entanglement detection, and then I will move towards the genuine entanglement detection criteria that we have proposed in our work, and after that, I will discuss the experimental realizations of our detection criteria, and finally I will conclude. So we all know that what is a bipartite entanglement? Suppose that there is an Alice and Bob. Alice has some system that is rho A, and Bob has system rho B in his and her particles. So if their joint state rho AB can be written as in the tensor product form, then we can say that the state is separable. If cannot be written as in the tensor product form, then we can say that Alice and Bob share some entanglement between them. So in recent years, it has been shown that entanglement serves as a crucial resource to perform several quantum information processing tasks, such as quantum teleportation, quantum superdense coding, etc. So when we talk about a resource, the most fundamental question that arises that how to detect that resource. So in this particular talk, I will firstly discuss that how to detect bipartite entanglement, and I will then move towards the genuine entanglement detection. And all to detect bipartite and multipartite entanglement, the most effective tool to detect entanglement is via positive but not completely positive map. Now, I will going towards the bipartite entanglement detection criteria. As I told earlier, that positive but not completely positive map help us to detect entangled states. Now, positive map. Now, I will discuss some basic, some initial stuffs about the positive map because it is required to continue my rest of the talk. So, positive map is an active area of research within mathematics, more precisely in the operator algebra community. And there are several foundational work in this direction in the span of 1960 to 98. Several seminar works has been done in this direction. Now, what is a positive map? Now, in this particular talk, we are restricted in D-dimensional Hilbert space, and we all know that in D-dimensional Hilbert space, all operators can be written as can be thought as a matrices. So here, my MD is actually representing set of all D square plus D square matrices in the D-dimensional Hilbert space. Now, lambda is said to be a positive map if it takes all positive elements to positive elements. That is, lambda is said to be positive if it takes all positive input row, positive output lambda row. That is, lambda row is greater equals to 0 for all row greater equals to 0. Now, I will give the definition of a R positive map. Now, if positive map lambda with some R dimensional identity, it also gives us positive output. That is mathematically, that is some R dimensional identity acting on lambda also gives us positive output for all rho greater equals to 0, and definitely for some R belongs to N. And for that R, we can say that lambda is that R positive map. Now I will discuss the definition of a complete positive map. Now, what is a definition of complete positive map? A positive map, lambda is said to be positive if it is R positive for all R. That is lambda identity tensor lambda acting on is greater equals to 0 for all rho greater equals to 0, and definitely for all R belongs to N. So this is the subset relations between the positive map, that is the positive map is actually the largest, completely positive map is the smallest set, and the R positive map is basically lying in between both. Now, from the definition of complete positivity, you can say that you can see easily that to check a map is complete positive or not, it is a very difficult task. Because here we have to check if it is R positive for all R belongs to N. So there are some infinitely such possibilities. So mathematically it is too hard. So to overcome this issue, there is a famous isomorphism called Choi-Yamalakasky isomorphism. And this isomorphism is actually an isomorphism between the language of operators to the language of positive numbers. So what this isomorphism is actually telling, that is corresponding to any positive map, we can construct a Choi operator. And what is the Choi operator? This Choi operator is nothing, this identity tensor lambda acting in 5 plus 5 plus. And if this Choi operator is positive semi-definite, then we can surely say that the map is completely positive. And if it is an if and only if relation. So if I getting my Choi operator is not a positive semi-definite operator, then we can say clearly that the positive map is actually not completely positive. Now we will go to the discussed. Now we will move towards the detection part of entanglement using positive. As I already mentioned earlier, that positive but not completely positive map help us to detect entangled states. So suppose that here for simplicity, I am taking transposition map. Transposition is a positive but not completely positive map. What transposition is actually doing? For any arbitrary input state row, that is row 1, 1, row 1, 2, row 2, 1, row 2, 2, transposition is actually flipping its off diagonal element. So that since transposition is a positive and not completely positive, it takes all separable input to positive semi-definite output. So therefore, if we get some not positive semi-definite output in my output state, then we can surely say that my input state is entangled. So this is the basic and celebrated detection criteria of entanglement in bipartite scenario. Now we will move towards the genuine entanglement detection. In real life scenario, entanglement can be distributed among many parties because of the quantum communication. Many parties can be involved, and they can share more intrinsic kind of entanglement, and this leads towards the concept of multipartite entanglement. So before means in this particular talk, I am not going towards the n-partite entanglement. For simplicity, I am considering only tripartite entanglement, but whatever I am discussing in the talk, it similarly can be extended to n-partite entanglement scenario. So in tripartite entanglement, suppose there is three parties, there is
Bi-
Alice, Bob, Charlie.
Bivas,
Yes.
make little
Yes.
faster. You have 5 more minutes.
Oh, yes, sure, sure. So suppose that there is Alice, Bob, Charlie, and suppose that they have not shared any entanglement between them. So their state can be said to be a fully separable state. Now it is possible that Alice, Bob can share some entanglement between them. Bob, Charlie can share some entanglement between them, and Charlie and Alice can share some entanglement between them. This kind of state are known to be a biseparable state. Now, any state which lies outside of the biseparable state is said to be a genuine entangled state. And this is the more intrinsic kind of entanglement. So, in this particular talk, our main aim is to detect genuine entanglement. Now, to detect genuine entanglement, this kind of positive map has been earlier introduced by several works by a work by Marcus Huber, Ritogdoto Sir, and they have earlier introduced a positive but not completely positive, which can detect genuine entanglement, and more precisely here tripartite genuine entanglement. Now, this is the positive map where lambda 1, lambda 2, and lambda 3 are actually a positive, not completely positive map. Now, here a K3 constant is used such that this map is actually giving greater equals to 0 for all biseparable states. So, therefore, if we get some negative output, then we can say that the state is actually genuine entangled. Now, for the transposition map in this particular work by Marcus Huber and all, for transposition map, they have proved that for A3 equals to 1, this map is actually giving a greater equals to 0 for all biseparable state. And for if we get some negative output, then the state is said to be genuine entangled. We also done some work based on some other kind of positive map using this kind of tripartite extension of the map. But there is a big challenge in this detection criteria that this kind of positive map are not completely positive. So this kind of positive map are not physical. So this kind of positive map cannot be realizable in a real experimental scenario. So in this work, we have defining some moments which can be realizable in the real experimental scenario. So corresponding to the transposition map, this is the tripartite map, and corresponding to this, we have defined this nth order moment. That is, we are taking nth power of the map and then calculating its quantity. And we have proved that if a state is biseparable, then all of its Hankel matrices are actually greater equals to 0. And what are the Hankel matrices? These are the some first two order Hankel matrices where S1, S2 are just nothing but the order of the moments. And these are some example of the first and second order Hankel matrices. But if the state is biseparable, all of its Hankel matrices are greater equal to 0. So if there exists at least one Hankel matrix which is less than 0, then the state is genuine intact. And we will show that this moment can be realizable in a real experimental scenario. So this is our proposal for realizing this moment. So this is the second order term of the moment. This is actually realizing the second order moment. This method can be similarly extended to realizable in nth order moment also. Here we are discussing about the realizations of second order moment. The second order moment term is actually reducing to these three terms. This is some 14, some constant term. So realizations of these two terms is the last two term is actually sufficient to conclude that the moment can be realizable in experiment. Now to realizations of the last term, now since we are calculating the second order moment, Alice and Bob has to take 2 copies of the state. Now Alice have to do swap measurement on her lab. Bob has to do some swap measurement on his lab, and Charlie also do has some swap measurement on his lab. And to calculate the middle term, Alice have to do 5 plus measurement on her lab. Bob has to do 5 plus measurement on his lab, and Charlie has to do swap measurement in his lab. So using this kind of approach, all the terms of the moment can be realizable, and this method can be extended. We have discussed particularly in our paper that all the nth order moment can be realizable using only this prescription only. So this is the summary and conclusion. So in this particular talk, we have discussed that genuine entanglement is also a crucial resource for several information processing tasks. So detection of genuine entanglement is an important before harnessing it to gain advantage. In this work, we provide a method to detect HDMI using moment-based approach, and our proposed criteria can be realizable in a real experimental scenario. So I would like to acknowledge my group members of SN Bose National Center for Basic Science. There is a large group here, and thank you.
Thanks, Bivas, for a nice talk. Now, questions. You can read the question in the chat box, Bivas.
Yes, okay. Just give me 1 minute. Okay, what is the role of quantum fidelity in teleportation? Means, am I understand perfectly? Do you want to know that can the quantum fidelity can be detected using the moment-based approach? Are you asking this question only? Hello? Yes, okay. Yes, means it can be means further area of research. Means yes, it can be in principle you can do it. We have not explored that area. That is to detect the fully entanglement fraction. This is for the fidelity actually. This is an a status fully entangled fraction greater than 1/d means it is actually useful for teleportation. So detect those kind of states is also an important task that can be detected using moment-based approach. We have not detected it, but yes, you can, if you are interested, you can do using this moment-based approach.
Okay, thank you,
Any
Bivas,
other?
once
Okay.
again for
Okay.
a nice talk.
Okay.
Our
Okay, thank you.
next participant is Miss Saheli Mukherjee from the same center, SN Bose. Saheli, you may
Yeah.
share your screen.
Thank you. So, am I audible?
Yes, you are audible.
Okay, thanks.
Bivas, kindly unshare your screen. Bivas,
Okay, give me a minute. I'm answering.
okay.
Yes.
I'll just put it in full screen. Yeah.
It's visible, but it's still not in full screen.
Yeah, I'm just starting that. Yeah.
Saheli, there is one thing, you have 15 to 16 minutes for the talk and then rest of the 3 to 4 minutes for the question answers, right?
Yes.
So
Yes.
you may start now in the full screen mode.
Yes. Sure. Is it full screen now?
Yes.
Perfect. Everything is perfect.
Okay.
Continue.
Okay, right. So, just a second. Yeah. So, hello everyone. Good evening. So, I'm Shahili Mukherjee, and as you have said, that I belong from the same institute, SN Bose National Center for Basic Sciences. So, I would like to thank the organizers for giving me an opportunity to present our work here. So, the title is Certifying the Dimensionality of Any Quantum Channel with Minimal Assumptions. So, this work is currently in archive, and this is done in collaboration with Bibhash, whom you have just listened to, and then Dr. Pratik Ghoshal, who is a postdoctoral fellow at HRI. Yeah, so then as you can see that there are several keywords associated with this talk. Certifying, dimensionality of quantum channel, minimal assumptions. So I'll be going through this part and then come to the main part of the talk. So the outline is that first I'll be talking about certification of resources. And since the resource here is the SMID number, so I'll give an introduction to SMID number and then quantum channels, and then I will propose our main certification protocols for the detection of those quantum channels. And then I'll conclude with some future plan. So certification of resources. So first, let us try to understand that why is certification necessary and what is certification. So for example, you have seen these bottles in the market about Bisleri. So there are numerous this fake variants. And also, I won't be surprised if you move around in the lanes of Kolkata and see Arsalan selling biryani for ₹90. But don't believe them, because there's a high chance that if you drink this water or this biryani, then you will fall sick. And also there are these variants of Adidas, which is currently sold as Adibas. So in order to identify that what are the resources and what are the fraud things coming out in the market, certification is necessary. So then how to certify? So one popular example might be the certification of gold. So whenever we go to buy gold, one of the ways that you look into the chemical composition of gold and I try to certify whether it is indeed a 24 karat or a 22 karat gold. But we are not professional chemists, so we do not know that. So then what to do? We simply look for this hallmark sign. And whenever we look for this hallmark sign, we know that, okay, it is authentic gold. So this is one way of certification we apply in our daily life. So then what are we certifying here? We are certifying the dimensionality of quantum channel. So dimensionality, we are quantifying by this SMID number. So then let me give a brief introduction to SMID number. So every bipartite pure state has its SMID decomposition, where the number of this particular non-zero terms are the SMID rank of the state. And this concept has always been extended for this mixed states as well, where the idea is that if you have a mixed state, then that mixed state you can write in a particular decomposition of pure states, and you calculate the SMID rank corresponding to all those pure states. You take the maximum of those values. So now, since this is a mixed state, you will have numerous such decompositions. And then you do this for all such decompositions, you get these maximum terms, and among them, you find the minimum ones. So
Mr.
then
Sush-
that gives, yeah.
Just wait. Mr. Sushil, kindly mute yourself. Mr.
Yes, sir.
Sushil, kindly
Yeah,
mute.
just now, sir. Just now, sir.
Yes, carry on, Saili.
So then you calculate the SMID number of this state. Okay, so this definition is provided in this paper by Terhel and Horodecki, and SMID number actually indicates the entanglement dimension. Yeah, so now why are we interested in certifying this? So higher SMID number is a resource actually. So people have shown in various of this task that higher SMID number is a resource for channel discrimination, quantum key distribution protocols, quantum communication, and so on and so forth. So then so we need to characterize this SMID number. So then this SMID number also has a characterization in terms of witness operators, where let us denote this set SR by the set of all such states which has SMID number less than equal to R. So by varying this different R, we get these various quantities S1, S2, and so on, where if R equal to 1, that means we have a separable state. So this is just a hierarchy of entanglement. You can think like that. So then all these particular sets, S1, S2, and so on and so forth, are actually convex and compact sets. So corresponding to each of these sets, you will get this hyperplane, which is the witness operator, which separates all of these sets from at least one state, which is of a higher SMID number. So that is the idea of a SMID number witness. And this is one particular witness proposed by Anna Sanpera and Matthias Levenstein in this particular paper. Yeah, so now having that, we have learned about SMID number of states and then how to characterize SMID number. So since I'll be talking about SMID number of channels, so then let's formally introduce quantum channel. So Bhivash has made my task easier because he has already talked about positive maps and then this Choi isomorphism. So just for the sake of completeness, let me just tour it in a very short time. So lambda is a positive map if it takes every positive element to some positive elements. And in addition, lambda is also a completely positive map if I take a maximal entangled state and then I feed one part of it through this map and the another part I feed identity through it and I get some output state. If it happens that the output state is also a positive operator, then the map is completely positive. And in addition, if the map satisfies the stress preserving condition, then it is CPTP map, which is a quantum channel. Okay, so now what is the basic idea? So the basic idea is we are talking about certification of channels. So Alice is this is a two-party task where Alice and Bob are there. The aim is that Alice wants to send some state with a higher Smith number to Bob. So, but because higher Smith number states are resource, so she wants to send a resourceful state to Bob. But let's say she sends this state through some channel. But if it is a very noisy channel, then even if Alice wants to send some higher Smith number state, this channel should have this ability to retain the dimensionality. So if it is a very noisy channel, then it may happen that it actually destroys the resource. So then we have to certify these channels that it indeed preserves the resource. Otherwise, Alice will send some state and it will be totally useless to Bob. So then this is the need to certify this non-R Smith number breaking channels, which I'll come to in a short while. But before that, let us try to understand that what are the certification protocols for this state. So the idea is that there is a referee who claims to send a state which is a resource. So here the resource is set of states with like Smith number greater than R. So this is my resource. So then how to do that? So the referee will assist Alice and Bob in certifying this state. So the referee distributes this state to Alice and Bob, who does local measurements on their part and then gets some output AB. So by repeating this process a large number of times, they generate this correlation. And from this correlation, they construct a linear inequality with these two properties. So these two properties are that the linear inequality is violated using a state of a higher Smith number and always satisfied by all states of lower Smith number. So then the idea is that by looking at this value of the inequality, you are able to say that whether the inequality is violated or not. And this violation guarantees that the state is of a higher Smith number. So then we have already done certification protocols for the state in this particular work along with our collaborators, which is published in Physical Review A. In that, we have shown that if you get to a Bell scenario, which is the device independent scenario, you cannot certify all higher Smith number state. But if you restrict your situation a bit and go to a measurement device independent framework where your preparation devices are trusted and measurement devices are untrusted, basically this is the semi-quantum non-local game. So then you are able to certify the Smith number of all states. So this semi-quantum non-local game is just like a Bell non-local game, where instead of classical inputs in a Bell scenario, the inputs are replaced by quantum inputs, and hence the name semi-quantum. So this idea was proposed by Francesco Buscemi in this particular paper. And so basically this DI certification works for all higher Smith number state. It does not work for all higher Smith number state, but this MDI works for all higher Smith number state. So by taking this motivation from states, we are trying to go to a scenario where we are able to certify channels. Okay. So now what we are trying to certify? We are trying to certify channels that does not break the Smith number. So those are called non-R Smith number breaking channels. So then what are R Smith number breaking channel? So this is the channel phi. If it happens that the output state after feeding in some input tensored by this ancilla is the Smith number of this output state is always upper bounded by R, and this happens for all input state, then this particular channel phi is an R Smith number breaking channel. Because you see the Smith number of the output is always upper bounded by R. It is always less than or equal to R. That is what it kind of reduces the Smith number. So hence the name breaking channels. So this was first introduced by Kruzinski and Koshakowski in this particular paper, who also showed that this R Smith number breaking channel admits a characterization in terms of Choi operator. So it has this one-to-one resemblance with this Choi operator. That means a channel is R Smith number breaking channel if and only if the Smith number of the Choi state is less than or equal to R. So then what we can do is, since we already have a characterization in terms of Choi state, we can just certify the Choi state because we have previously seen the certification protocol for state. We can just apply it. But this comes with some limitations. So Choi state, as you can see, it requires the preparation of this Maxwell entangled input and perfect identity channels. So additional requirements are there. And also, people have used this particular formalism for certifying other channels, which are these non-entanglement breaking channels. So this entanglement breaking channels has a beautiful form. It can be written in a measure prepare scenario. So then you can use this particular properties or the Choi operator kind of things to certify. But that comes with some limitations, that is lots of resources are consumed, or for some channels which do not possess these properties, like they cannot be written in a measure prepare form, or we do not know, we cannot apply this formalism. So then what about channels that do not possess such properties? So then comes with our scenario of minimal assumptions. So the minimal assumption, because we do not assume that the channel holds such properties, or we do not assume the preparation of maximally entangled input state as required in the choice state certification. So the scenario is that there is a referee, there is Alice and Bob. The referee sends some quantum states to Alice, which are denoted by this psi xa, which are non-orthogonal quantum states. And these states come with probabilities p psi xa. So Alice now sends this state to Bob through this quantum channel n, whose Smith number we actually want to certify. And then the referee also sends some non-orthogonal quantum inputs to Bob, which are this phi yb, and these inputs come with these probabilities. So now Bob has these two-partite systems in his lab, and then what he can do is he can do this joint measurement M and get some output B out of it, which he communicates to the referee. So by doing this process a large number of times, they can generate this correlation PB given psi xa and phi yb. And then from this correlation, as you know that all of Bell inequalities are basically functions of these correlations. So here also, from this correlation, they can generate some payoff function and calculate the average of that payoff function, which is I average. Then the idea is that for all R Smith number breaking channels and whatever measurement Bob performs, this payoff function is always a positive. And then if we get at least one measurement for which the payoff function is negative, then we know that the channel is definitely a non-R Smith number breaking channel. So then kind of for this scenario, one does not need to know quantum mechanics or anything. They just play this game, and the value of the payoff function kind of divides this R Smith number channels with non-R Smith number channels. So the beauty is that this works for all non-R Smith number channels. So sorry about this notation. So sometimes I'm using K and R, although they mean the same thing. So the idea is that for all non-K Smith number breaking channels, you will be able to construct such a game for which the payoff of that game will be negative, whereas for all K Smith number breaking channels, the payoff will always be positive. And this works for all channels. And this is a measurement device independent framework, because if you can see the scenario that this psi xa and phi yb, these are actually trusted quantum inputs. So the Alice and Bob need to trust this, that these states which are coming to them is actually psi xa only and not some psi xa prime. And this is also phi yb and not some phi yb prime. But the measurements, there is no trust on the measurements. So this is a measurement device independent framework. Okay, so then if we try to understand that what are the key properties which are helping in the certification. So one of the key properties is that these kind of channels have a one-to-one resemblance with Choi operators. And another key property is that if E is a K Smith number breaking channel, and then you concatenate it with some CP map, then the concatenated thing is also a K Smith number breaking CP map. So these are the two properties that are actually enabling the certification. So then to summarize, we have studied the certification of non-R Smith number breaking channels in the measurement device independent framework. And we have previously shown that the device independent framework does not work for all states. So you can just take the choice state corresponding to that channel, and the device independent framework will not work for all such choice state. That is why traditional Bell games fail to certify all non-Smith number breaking channel. So in order to certify all non-R Smith number breaking channel, we relax the situation a bit and we come to this measurement device independent framework, where we see that the certification works for all channels. And then our scenario is also based on minimal assumptions, because it does not require the preparation of maximally entangled states and perfect side channels. So then we have studied the certification of channels which are possessing these two beautiful properties. It will be interesting to see the certification protocols for channels which does not possess these two properties. And so in any operational theory, there comes preparation, transformations, and then measurements. So we have already studied states and channels. So the remaining thing is that if we are able to design some certification protocols for certifying the Smith number of measurements. So with that, I would like to thank my supervisor, Professor Archon Mojumdar, and the entire quantum information group at our institute, and the background slide, as you can see, this is a view of our institute, which is currently in Kolkata, Salt Lake. And I would like to thank my institute for giving me this institute fellowship and for all the amenities I'm provided for my research. So
Okay,
thank you.
thank you, Sally. There is a question in the chat box, please.
Yeah, sure. Just a moment. Uh,
Question is, what is a semi-quantum non-local game and how is it different from Bell tests?
yes. Yeah. So semi-quantum. So as you know that in Bell test, the inputs are classical and the outputs are also classical. Okay, but in semi-quantum non-local game, the inputs are quantum inputs and the outputs are classical. That is why it is semi-quantum. So the idea is that, and these inputs which are quantum inputs, they are non-orthogonal. And because if you see that if you take orthogonal inputs, then there will always exist some measurement by which you can distinguish the inputs, and then it will reduce to some traditional Bell games only. So that is why, to make sure that it is different from traditional Bell games, the inputs are non-orthogonal. So that is the idea of a semi-quantum non-local game. And any non-local game, any game you design using this quantum inputs and classical outputs come under the domain of this semi-quantum non-local games. Yeah.
Okay, let us thank Sally for a nice talk.
Thank you.
Kindly unshare your screen. And our next speaker is Debarti Paul from ISC Bangalore. Debarti, okay. Kindly share your screen.
Yes.
So whose screen is visible? Is it Vibhash still visible?
Bivas.
Vibhash has not unshared still.
Mm,
I'm sorry, I'm just in. I don't know what is the problem is going on. Yes, I think it's fine now.
Okay. So next speaker may kindly share her screen.
Yes, I'm trying to share my screen. Uh,
So till you start, I just want to share a comment for the last speaker. Means the starting was very nice. I mean the examples which you gave for certification was very beautiful.
Thank you, sir. Thank you so much.
I think I have to leave the meeting and join again to share the screen.
Okay. But do it quickly because
Sorry.
your time is going. Perfect. Just make it full screen and start.
Yeah.
Your presentation is gone. Now we can see you, but not your presentation.
Sorry.
Do it comfortably. Don't be pressurized.
Yeah. Think, is it visible now?
It is visible, but it is not full screen. Now it is full screen. Perfect. So just
Full
start
screen?
talking.
Okay. So good evening all, and thanks for giving me the opportunity to present for today's talk. And today my topic is folding free zero noise extrapolation by layout induced noise diversity. And this work is there on arXiv. You can check it out. And this work is done with my professor Yogesh Simhan and Dr. Ritajit Majumdar from IBM Quantum, who gave detailed discussion in developing the problem statement and setting up the algorithmic and experimental strategies for this work. So in the starting, I would like to introduce standard ZNE. Before we understand what is zero noise extrapolation, we already know that quantum computers are extremely noisy. And in the current scenario, practical implementation of full fault tolerance is not possible. So this constraint motivates us to use error mitigation techniques in order to recover the accurate expectation value. And one such method is zero noise extrapolation or ZNE. And we are calling the existing ZNE here as the standard ZNE, where we first amplify the noise in the quantum circuit and then extrapolate it to the zero noise regime. And with this, we get the expectation value of the observable in a region having zero noise. We insert additional quantum gates in the circuit to amplify the noise of that circuit, and this we call folding. Now, there are two ways to fold the quantum circuit. First is local folding, where each of the gates are folded such that we have U as the original gate. And then there is U and U dagger, which does not change anything since U dagger U becomes identity. And the second type of gate folding is global folding, where the circuit as a whole is folded. Now, when we talk about the amplification of the noise and extrapolating it, the standard ZNE faces some challenges, and those are first the choice of the noise scaling factors lambda, and secondly the choice of the extrapolator, whether it should be exponential or linear or polynomial degree 2, etc. And it can be anything. And currently, when we use zero noise extrapolation in IBM runtime, the default noise factors are 1, 3, and 5. And it has been observed that as the circuit size grows, these default choices does not produce accurate results. And you can see it from this example. Suppose we have a mirrored QAOA circuit, and this is a mirrored QAOA circuit of 8 qubits. In this circuit, we are measuring the expectation value of an observable, which is a weight 1Z observable. And since it is a mirrored circuit, the ideal expectation value is always +1. Now, when we do the error mitigation for an 8x4 circuit, which has 8 qubits and 4 as a circuit depth, and we use linear extrapolator with the default noise factors of 1, 3, and 5, then we get the mitigated expectation value as 0.9920, which is pretty close to the ideal expectation value. And then when we change the extrapolator to polynomial degree 2 and exponential, then the mitigated expectation value doesn't change much, and it is still close to +1. So it is fine till now. After that, when we increase the circuit size, for example, we increase the number of qubits to 40 and the circuit depth to 40, then for the same default noise factors of 1, 3, 5, we get 0.5814 as the expectation value, which is quite deviated from the ideal expectation value. And with the exponential extrapolator, when we change the extrapolator from linear to exponential, it becomes worse. It becomes 23.8150. So in order to get close values to the ideal expectation value, we take another noise factor, which is 1, 1.2, and 1.4. And with the linear extrapolator, we get 1.2644 as the expectation value, as a mitigated expectation value, which is pretty close to +1 again. But for the as we change the extrapolator to exponential, it changes drastically and it becomes very bad in order of 10 to the power 24. So with this example, you can see that the selection of the noise scaling factors and the choice of the extrapolator, it matters so much in standard ZNE. And the current best practice that we use is first we Cliffordize the circuit so that we can find out the ideal expectation value, and there are some hardware constants. So we have to Cliffordize the circuit first, and then we try different noise factors and extrapolator in a hit and trial method. But this has disadvantages because quantum overhead increases. Since for trying different noise factors, for example, if you try one noise factor of 135, then we have to execute 3 quantum circuit on the hardware. So for 20 trials, we have to execute 60 quantum circuit on the quantum hardware. So the quantum overhead increase is so much. But still, it doesn't guarantee that we will find the best noise factors, since we are able to only try a finite number of cases in the choice of the infinite number of cases. And also, performance depends largely on the experience. For example, one noise factor can be good for a circuit and it cannot be good for another circuit. So it depends largely on intuition and experience, whether the noise factors are good or bad. Now, there are some existing approaches to address the parameter selection problem. Suppose, for example, evaluating the multiple noise factors and extrapolators using RB circuits, but these have a lot of disadvantages, and our work tackles with the disadvantages. And to overcome these problems of experience, intuition, and hit and trial, we have used an approach in our work where we use the noise profile of a quantum hardware. And this is a 27 qubit quantum hardware. And in our work, we have used 133 qubit quantum hardware, IBM Torino. From this picture, we can see that different qubits and connectivities have different noise values. For example, this qubit is noisier than this qubit, and this connectivity is noisier than other connectivities. So the conclusion is that the noise profile is not uniform in a quantum hardware. And we are using this non-uniformity in our technique to get a folding-free zero-noise extrapolation, or FFZNE, where finding the noise amplification factors using folding is not required anymore. Suppose we have 10 qubit circuit and we can map the circuit to a hardware in 3 different ways. More than 3 ways actually, but taking the care of the space, I've only shown 3 layouts, and they are called the isomorphic layouts. Due to the non-uniformity of the noise profile, the first layout will have a score S1, where the score is a function of the noise profile of the layout. For the second layout, the score is S2, and similarly S3 for the third layout. And these are the different scores based on the layouts. Now, instead of using gate folding as our noise amplification technique, we are using the noise profile of our hardware as the amplification method, as shown in this graph. Layout scores obey to a linear extrapolator. Thus, the problem of finding good noise amplification factors reduces to finding proper layouts. Now, before coming to the algorithm that finds such layouts, we should know about the requirements that algorithm should follow. The first requirement is that the layout scores should be equidistant to each other. Why? Since this noise model is stochastic Pauli, and so we will use a linear extrapolator, and thus we need equidistant point. The second requirement is that the scores that the algorithm will give must cover majority of the spectrum of the isomorphic layouts. Since if we don't cover the majority of the spectrum, we will only perturbing a small section of the noise spectrum, and we won't be able to exploit the non-uniformity of the noise profile. Also, if the points are too close, then the expectation values will be close, and we won't be able to do reliable extrapolation. Also, some of the qubits and connectivities in current quantum devices are significantly more noisier than the general noise profile, and therefore we're not accepting layouts whose scores are 1, since this means that the qubit is not working at all. And also, we only take those layouts whose scores are within 3 standard deviation from the mean score. Taking care of these requirements, the first algorithm that we used in our work is exhaustive search, where we fixed the first layout that has the lowest score and hence it is least noisy, and then searched for SI and SJ such that the difference of the scores remains same. And the time complexity in this case is order of m square, where m is the number of isomorphic layouts. The algorithm worked pretty well until we tried for the 40 qubit efficient SU2 circuit on IBM Torino, which is a 133 qubit quantum hardware. For this, the number of isomorphic layouts came out to be around 16 lakhs. And to find out the 3 desired layouts, the algorithm took more than 6 hours. And so this is too costly, right? And after to deal with this, we used binary search algorithm. And the time complexity for this is order of m log m, and the same 40 qubit efficient SU2 circuit only took 2.2 into 10 to the power minus 5 seconds. And it makes the classical pre-processing time required for our method feasible. Now we have the 3 layouts on which we will run our circuit, and we can finally visualize the hardware results. But before that, I would like to show you a 6 qubit efficient SU2 circuit, and which is a sparse circuit, and also a 6 qubit Hamiltonian simulation circuit, which is a dense circuit. And our hardware results are for these circuits with up to 50 qubits. This is the hardware result for the 50 qubit efficient SU2 circuit. The 2 qubit depth for repetition 1 is 49. And for repetition 2, we were able to go up to the 2 qubit depth of 98, which is at the state of the art. The green bar is the ideal expectation value, and the orange bar is the mitigated expectation value. The results, even for 2 qubit depth of 98, are pretty good with average deviation of around 6% from the ideal. Now, problem arises when we try to find out the layout scores of a dense circuit, that is the Hamiltonian simulation circuit. From the table, we can observe that for the same 20 qubit circuit width, Hamiltonian circuit's layout are decaying fastly to 1. And for repetition 3, the scores are very close to each other, making the extrapolation unreliable. Therefore, we need a new scoring mechanism. And for our work, we used quality indicator circuit scoring mechanism, where QIC is a circuit which has the following properties as stated here. And more information about QIC can be found from this reference. Now, when we used QIC scoring method, the results were pretty impressive, as you can point out from this table. For 20 qubit Hamiltonian simulation circuit, using QIC scoring method yielded expectation values which are really close to the ideal expectation value. Whereas Mappomatic scoring resulted in high deviation as we increased the number of repetition, that is the circuit depth. Also, the Mappomatic scoring method resulted in even worse expectation values for the 50 qubit circuit, whereas performing ZNE with QIC scoring method yielded expectation value close to 1, making FFZNE scalable. Now, coming to an end of the slides, the summary of the folding free ZNE is that standard ZNE, as explained in the first slide, is very widely used mitigation technique. ZNE depends heavily on the choice of the noise factors and extrapolator, making it useful for people with prior experience. But our proposed FFZNE does not require the above factors since we used isomorphic hardware layouts. We found only a deviation of 6% from the ideal value for a 50 qubit sparse circuit and 4.5% of deviation for a dense circuit. So we were able to find good results for utility scale circuits. FFZNE does not require any prior intuition to select the noise factors and the extrapolator. Thank you.
Hello, ma'am. Hello, ma'am. Am I audible?
Yes, you are audible. Ask your question.
Okay. Ma'am, you explained that ZNE, I think zero noise exfoliatory, maybe. I just want to ask, you explained local folding and global folding, in which we will use gate to to reduce noise. Noise. ठीक है, ma'am. I want to ask that would you like to differentiate which one is better, local folding and global folding? Like local folding, we are taking some small part to reduce noise, and global folding, we are taking whole circuit. So which one is better in which condition? Would you like to differentiate difference between two?
Overall, you can use any of the method for folding, but from the results and from the prior results that has been seen, the global folding has given much better result because we are using the whole circuit for folding. But local folding is also useful for noise amplification, so you can use any of them. So
Ma'am,
it's a hard
basically,
constant. Yeah.
Local folding, in case of we are reducing from every parts, like something take small parts, okay. So in this situation, we will reduce noise more better than, I think, global, because global folding, like a whole circuit, they are reducing noise of whole circuit, like not for a small part, like something small part is better than a whole.
Yes, if you want to dig into each of the gates, then local folding is better in that case. But global folding is also useful in many of the cases for noise amplification, and also in partial folding, you can use both of the folding methods.
Thank you, ma'am. Your presentation was very informative. Thank you, ma'am.
Devarti, there is one more question in the chat box. Why does QIC perform better in dense Hamiltonian circuits?
Yes, in the dense Hamiltonian circuits, as I have shown you in the slides, that the scoring mechanism, the scoring for the 20 qubit Hamiltonian circuit, the scores were becoming very close to each other, and therefore the use of the linear extrapolator was unreliable in that case. But using QIC scoring mechanism, we have seen that the scoring is not just exponentially decaying to 1 so fastly, and it is slowly decaying to 1, and that's why QIC scoring method for dense circuits, where mathematic scoring method that we have used earlier was not performing well due to the fast decay to 1. But in QIC scoring mechanism, it is slowly decaying to 1, and thus resulting in better scoring and better extrapolation, and that's why it is more helpful to use QIC scoring method for dense circuits.
Okay. Any other question? Okay, there is no question now. So thank you,
But
Devarti.
we can keep things now open for, because this is the end of the session and next session is 7-8 minutes due. So
Okay.
if any of you have questions from the previous speakers which is not answered because of scarcity of time, or you can make some general comment, discussion.
Devarti, you may unshare your screen.
You can do that. Means if anyone wants to make any comment, those who are not a speaker, or because this is a break. So in principle, we are in 10 minutes break. So what we do in a real conference during the break? So in a real conference during the break, we interact with each other, we discuss with each other. So virtually, if you want to discuss, you want to ask. So some questions are left. Normally in a normal conference, we say that, okay, during tea time, you ask it. So consider this as tea time. And if you have a question for Dr. Kishore Thapliyal or anybody, you can ask. Just now I can see that there is a, why do dense circuits reduces score? So just see, means this is for the last speaker. You can answer, and if there is another question for anyone else, but others who want to take a short break, or you can, and then the next talk will be at 7:30. So can you answer the last question? If there is one more
Devarti,
Yes.
can you answer this question? Why do
There's one
dense
more question.
circuits reduce score distinguishability?
Yes, for the dense circuits such as the Hamiltonian simulation circuits, there are more gates than there are in the sparse circuits, and that's why the noise is more, because the number of gates are more. So the distinguishability reduces because the noise is increasing drastically in dense circuit. Therefore, for just a small difference of the circuit width, the scores are really higher in number and they are more near to each other. So that's the reason for reducing score distinguishability for dense circuits such as Hamiltonian circuits. I hope this answers your question.
Thanks, Devanti.
Devati, may I ask a question?
Sure, please continue.
Yes.
Yes.
Devati, okay, from the expectation value point of view, you are observing that after the mitigation of errors, you get quite close to the what is the without error. So, did you also try to check with what happens with the probability distribution? That also remains quite close, or?
No, I haven't checked for the probability distribution, but yes, we can check that, but till now we haven't done that.
Okay.
Yes.
So, because when you are applying, you are applying random circuits, so and randomness is not perfect. So even if you are applying U and U dagger, ideally it may not cancel out each other. So I expect that the probability distribution may not get such a perfect result. So
Yeah, but I would like to answer this. It's actually, we are not using folding anymore in our technique. We are using the isomorphic layout. So there's no question of folding. So this is not a problem anymore, because for the folding case that was happening in previous ZNE, it was really it was really random to get a noise factor. It was completely hit and trial method to get the perfect noise factors. But in our case, we are not doing the folding. So even in random circuit, we will just run the circuit on different isomorphic layouts, and then we will use the scores of those layouts and then extrapolate it to the zero noise limit.
Okay.
Yeah.
That looks at least more reasonable.
Yes.
Any other general question or comment from anyone? Anything for discussion? So,
Sure, well, I do have one
let's
question.
please.
Good evening. Well, it is not related to only physics, but I really wanted to know about quantum. So my question is like that, sir, we often say that quantum computing is more about unhackable thing. And first thing, and
More about?
We often say that quantum can make a unhackable distribution systems, right?
No one has ever told that.
Uh,
You have never read such a statement. So what is told is it is unconditionally secure, but unconditional security does not mean unhackable. So what is the difference, to address your query and to clarity? Like when you do this class, suppose, because we have 3 minutes, so I'm just slowly answering you. So algorithms have nothing to do with computer. First algorithm that has been taught to us, you, me, and most of us, is by our mother when we learn to do addition. So somebody told us that suppose you have a 2-digit number, write a 2-digit number, another 2-digit number below that, but write it in a way that unit place is below unit place, 10th place is below 10th place, 100th place is below 100th place, and then you add one by one. So this is a systematic procedure. And now you see, if you have 2-digit, you have 2 steps, 3-digit, 3 steps. So that number of steps we have to count in an algorithm. So if the problem size increases to n, how the number of steps increases. So if that happens in n square, n cube, or any polynomial or less than a polynomial, say log n, square root of n, we say that these problems can be solved efficiently. Now there are problems whose solution can be checked efficiency, but it is not known that whether they can be solved efficiently or polynomial number of steps. Such problems belong to a class called NP, and the problems who can be solved in polynomial number of steps are in P. Now, if I fetch a problem from NP which is outside P, then and make a cryptographic problem, then these are classical cryptographic background. So we use something like odd biprime factorization. It's a difficult problem. You take 2 very large prime number, multiply, do some transformation, and give me, and I have to factorize. But if I tell you the factor, you can check the factor whether it is correct or not in polynomial time, but you cannot solve the problem in polynomial time. Now, quantum mechanics can help you to address this, say, solve this problem, odd biprime factorization. So if a scalable quantum computer is there, then RSA cryptography will be broken or vulnerable. So
Okay.
here the security is coming when you are even claiming now you are sending something with 128 bit or 256 bit. You are assuming that your enemy, Eve or somebody, some eavesdropper, does not have computational facility, another algorithm or a better computer with which he can hack it or do the factorization, solve the discrete logarithm problem. So it's conditioned on, the security is conditioned on somebody else's computational power. So I
Uh,
give you another example. There is a
okay.
problem in cryptography called remote coin tossing.
Okay.
So I have to toss a coin, and you and me are in two different places, and we don't believe any third party. We don't like each other. I don't want to see our face, but we want to toss a coin. If you send me the bet first, I'll tell you that, okay, this is not the outcome. If I tell you the outcome first, you will tell that that was your bet. So classically, the solution is I toss the coin, put it in a box, lock the box, and send you without sending the key. Now you send me the bet. Once I receive the bet, I send you the key. Since the box was already with you, I cannot change the outcome, and you have already sent me the bet, so you cannot change. But now you see, intrinsically, there is an assumption that when it reached you, you cannot break the lock. So I'm
Exactly.
assuming a condition on your power. If it is a physical lock, you cannot break it. Your muscles are not that strong. You don't have such a strong hammer. Or if it is a digital lock, your computers are not. So this is called unconditional, conditional security. In contrast, quantum is not based on such a assumption on somebody else's computational power. Rather, the security comes from laws of physics, like no cloning theorem, Heisenberg's uncertainty principle, superluminal communication is not allowed. So this is unconditional, but unconditional does not mean unhackable. So where from the hackability comes? The hackability comes from device imperfections. The device we use to implement a quantum cryptography are not perfect. You have a single photon detector, which has certain efficiency that normally works in Geiger mode. But if you send an intense light, it will start working in a linear mode and it will become blind to single photon. So that's the called detector blinding attack. So here the notion of hacking will be changed. Hacking will be using the limitations of devices, but it's hackable. It's not unhackable. It's unconditionally secure. But of course, the best position will be device independent quantum cryptography, which will be independent of even the device imperfections, but that would require the kind of detectors which we don't have at the moment. So at the moment, the best thing on which is possible is called measurement device independent quantum cryptography. So what you are saying that we often say, we don't say that often. What we
Okay.
say is unconditional security, not unhackable. So these two things are different. But anyway, we can continue this discussion sometime else. Now it's time for start moving for the next session. So
Thank you so much, sir.
we would like to thank all the speakers of the first session as well as the session chair, Dr. Amit Verma, and would like to move for the second session and invite Dr. Chitra Shukla, who is right now in Luxembourg, at Luxembourg University. Earlier, she did PhD with our group, and then subsequently she was in many places. She was a JSPS postdoctoral fellow at Japan. Then she was for many years at China at different places. Subsequently, she was in Luxembourg. So she's a very bright young quantum scientist who has vast experience, and it's not about sharing about the session chairs or speakers, but rather to move with the new results which young scientists have produced. So without further delay, I hand over the session to Chitra and request her to conduct the rest of the day's proceedings. Over to Chitra.
Thank you, Professor Pathak, and I really thank for this opportunity to chair this session, quantum communication. So so let us begin with our first speaker is Mr. Vaishak from University of Vigo, Spain. Mr. Vaishak, are you there?
Yes, I am here. Can you hear me?
Yes, we
Yes.
can. Yes.
Share your screen.
Sure.
Yeah, please share your screen.
Okay. I hope you're seeing my screen and seeing the slides change.
Yes.
Perfect.
Okay.
Continue.
So
Everything is
okay.
fine. You continue, but we cannot
Sure.
see you. If you are confident on your network, you can switch on your camera as well, if you are comfortable.
I'm not so confident. I'm outside right now. I'm actually attending an in-person conference. And,
Please continue.
okay, so thank you for the invite for this giving this talk, and I'll be talking a little bit about the research that I've been doing at University of Vigo. It's related to some of the mathematical tools we use in proving QKD security. And yeah, first I would like to acknowledge my collaborators, without whom it would have been impossible to come up with these results, and they're responsible for the results that I'm going to share here. So first of all, my supervisor, Marcos Curti, the postdoc that I'm working with, Victor Zapatero, NICT director from Japan, Gokato, and Professor Kiyoshi Tamaki from University of Toyama in Japan. Okay, so what is concentration inequality? It's basically a tool that we use to bound the deviation of a random variable from its expected value. So imagine that you have a distribution that looks like this. And if you sample from this distribution repeatedly, you will notice that most of the time the random variable comes from the central mass of this distribution, because most of the probability lives in that particular region. What concentration bounds enables us to do is to calculate an upper bound of the probability of the tail region, which I've marked here in red. So this tail region is defined by the values of random variable x greater than a certain threshold value or less than a certain threshold value for the upper and lower tail respectively. So the concentration inequalities helps us to bound these tail probabilities, and this is essentially helpful for us to come up with upper and lower bounds for the variables of interest. And yeah, the tail probabilities helps us to, let's say, assign some failure probabilities to these upper and lower bounds. Now, let's first look at one of the most important tools that people use to come up with this tail probability evaluation, or the upper bounds for the tail probability. So this is exactly the Markov inequality that you see on the screen here. So first I want to give you a bit of an intuition why this statement, which holds for any positive random variable x, should hold true. For that, I utilize this diagram here. So on the x-axis, I'm plotting the values of the random variable x, and I have two functions here, f of x and g of x. So f of x is the indicator function. So basically, it's a function that outputs 1 if the random variable value is greater than a, and it's 0 everywhere else. And then there is another function g of x, which is like a function that upper bounds f of x at every point. So take any value of x, g of x is greater than f of x. Now, if you take the expectation of both functions, you will see that this is exactly the Markov inequality, right? So this is like an intuitive graphical explanation of why Markov inequality should hold true. Now, instead of this function g of x, we could have chosen a more sophisticated function. Okay, so this is like I'm going to represent the Markov inequality in this form just for convenience later on. Okay, now we can choose a more sophisticated function like this. So this is an exponential function and with a tuning parameter t, right? Now we can use the same technique that we used before, take expectations of both functions, and we'll have something like this, which looks very similar to the Markov inequality, but with an exponential function within it. Now this tuning parameter t, which I've introduced here, is really important because when you change the t, the form of the function changes. And why is this important? This is important because the inequality that exists inside the Markov inequality with the exponential, which I'm going to call as the Chernoff bound from now on. Okay, sorry. Yeah, so we want this inequality to be as tight as.
Speaker to mute.
Anirudh, please, could you? Anirudh Kumar, could you please mute yourself? Yeah, okay. Please go ahead, Vaishak.
Okay, so as I was saying, we want the inequality to be as tight as possible, and this happens when the expectation of f of x and g of x sort of closely matches. So the tuning parameter t helps us to achieve that. So with the right choice of t, we can get the expectation values to match as close as we can. Of course, it won't match perfectly, but if you get close enough, for most problems, we are satisfied, right? Now, let's look at the specific distribution. So we'll focus on the binomial distribution because it's very simple and it will give us some very neat results that we can build upon later on. So again, I've drawn the distribution and the tail event of the distribution. And the idea is, okay, so you have the parameters of the distribution. We have the Chernoff bound that we just constructed for this distribution. And the objective is to minimize this upper bound A such that the tail probability is less than some predefined failure probability epsilon. So we want the upper bound to be as small as possible so that you see so that we can, so that the random variable is as close to the expectation value as possible. So we want it really to be concentrated around the expectation. So we want the upper bound to be as low as possible. And if you were looking at the lower tail, then we want the lower bound should be as high as possible. So we want it to be really close to the expectation value. Now, this can be solved efficiently. So we can tune the value of t using some calculus, and we can use some lower and upper bounds for the exponential function to come up with some very neat representation for a. So we can write a as a function of all the known parameters. And I'm not going to show the actual expression here because that's not very informative. But nevertheless, what we end up with finally is an expression that looks like this. So probability statement that the random variable x greater than some function of p, which is the binomial parameter, is bounded by epsilon. Now, if the function gamma that I've defined here, that I've mentioned here, if it's neat enough, you can also invert it, and you'll end up with a statement like this, which essentially gives us a lower bound for the population parameter p. So this is of the form p less than some function of the random variable, which is bounded by epsilon. Okay, and we were just looking at the upper tail. We can also take a look at the lower tail. It's a symmetric case, and we'll come up with two more bounds. So these are the two bounds. And again, the idea is that you have the random variable, you have the binomial population parameter, and you want the upper and lower tails for both of them. So you will end up with 4 bounds. And this is what we expect from a concentration bound. We want to come up with such these 4 bounds. Okay, now we have the binomial distribution and its associated bounds. Now, in QKD when proving the QKD security and coming up with the key length equation for QKD, sometimes you'd have to estimate some parameters and you'll have to calculate the bounds of those parameters, which are following certain distributions. So binomial is one of them. So I'm sort of explaining the binomial as a simple sampling ball from a box example. So in the binomial can be explained by, okay, you have if you have n trials, we associate n boxes, and every one of those boxes have the same distribution of balls. So in this case, I've drawn 3 boxes. So and the 3 boxes have the same distribution of the red and green balls, and you're sampling each ball from one of these boxes one at a time. So this is a sum of IID Bernoulli setting, and this describes the binomial distribution. We could also have a Poisson binomial distribution where, again, we are sampling one ball from one box each, but the distribution of the balls inside the boxes are different. So in this case, you'll see that the 3 boxes are different. So this is a sum of independent Bernoullis, but they are not identically distributed. So the distribution is not the same. The distribution of the balls inside the boxes are not the same. You can also have the hypergeometric distribution. In this case, you are sampling a ball from the box, but then you are not putting it back in. So with each round, the number of balls in the box reduces, and the distribution of the balls will vary depending on what outcome you observed in the previous rounds. Now, these distributions are typically what comes up in, for example, when you calculate decoy BBAK4 protocol key rate equation, for example, right? And and we need to come up with confidence bounds for this distribution. So we already saw the confidence bound for the binomial, but we need to come up with it for a Poisson binomial and hypergeometry. But fortunately, there is a couple of results from the last century by Vasily Höffding, which states that once you have an exponential bound for the binomial, you can pretty much use it for bounding the Poisson binomial and the hypergeometry. So we are pretty much done. Like if we are only considering these three distributions, we already have what we need, right? We can apply the results directly to QKD protocols and calculate the key rate with this new developed or this new advanced bounds. So I'm showing an example of a QKD key rate plot with these bounds applied. So this is a DBM92 protocol. On the x-axis, we have the block length, and the y-axis, the finite key rate. Shown in yellow is the Surfling's inequality, which is used for bounding the hypergeometric distribution. And the hypergeometric distribution is important in QKD because this is what we use for bounding the phase error rate based on the observed bit error rate in the complementary basis. And the red and blue lines are the numerical and analytical versions of our bounds that we just saw. And the vertical line in the inset, the inset plot is the block length that was observed in the Michias experiments. And we are using the same parameters that they've used in their experiment. So this is like a physically relevant, or let's say a realistic choice of parameters. So there is no cherry picking of parameters just to show that our bound is better. So this is like what we observed in the real world when we conducted an actual satellite QKD experiment. And we see that in the small block length regime, which is the inset plot, there are block lengths for which the traditional tools won't give any key, whereas our tools will give a positive key. And even in the large block length regime, up to 1 million blocks. So these are like detected blocks, right? So these are like detected signals. So 1 million is like absolutely huge. And you see that even in those regimes, we see an advantage of our methods compared to the traditional methods. Recently, one of my colleagues within my Marie Curie PhD network was also part of a couple of experiments where he was able to apply my bounds directly in his experiments. And the experimental plots show the same trend as the simulations. So the red line is the key rate plot, and the Chernoff, labeled as Chernoff, is the bound that we just saw, and Surfling is the traditional bound. And we see a 10 to 20% increase in key rate just by switching up the equations or the bounds. And more importantly, he also simulated the secret key or the secure key that you can calculate from a satellite overpass. So on the x-axis, we have the time of data acquisition, and on the y-axis, we have the cumulative bits that you can extract. And here, the important fact here is that if you choose for a smaller block length, so if you choose for 10,000 sized block length, you will get a higher key rate in the initial stages of data acquisition because the data is not, let's say, large enough to accommodate a block length of 10 to the 7. So only after the 300 second mark can we actually extract key from a larger block length. And even then, the key rate is or the cumulative bits that we get from using a small block length with a large block length is pretty similar. So this is really good news for us because our bound, as we saw earlier, is like really good when the block length is small. So for satellite QKD, maybe our bound can really outperform all other traditionally used bounds. Okay, now let me talk about a bit more recent result that we obtained. So the idea is to extrapolate the bounds that we just saw, but to more general probability distributions. So this is known as the adaptive process protocol or the adaptive distribution, where each Bernoulli variable xi is dependent on the outcomes of all the previous trials. Right. So again, I'm using the ball and the box analogy. So here, depending on whether you get a green or red ball, the next trial will vary. Like, so the distribution of the balls inside the box in the next trial will vary based on the previous outcomes. Right? So if you think about it, this adaptive process can describe all the other distributions that we just saw. So the binomial or a Poisson binomial or a hypergeometric distribution can be thought of as a special example of this adaptive process. And in this process, in this adaptive process, what we want to look at is the concentration of the random
Wait,
variable x around the
Vaisak,
sum of conditional expectations. Yes.
just you have like 2 minutes more, or so please, could you please wrap up soon
Okay, sorry.
so
Yeah,
that we
no
can
worries, no
have a
worries.
question
Okay,
answer
yeah.
as well.
The idea is to come. Yeah, I get it. Okay.
Mhm.
Okay, so yeah, essentially, we can actually use the same techniques that we used before to come up with the bound for this adaptive case as well. There are some roadblocks and issues that we need to solve, but essentially, since we are short on time, I'll quickly go through it. Essentially, what we get is that we have a technique in which we can just assign a range of guesses that you can assign for this adaptive process for what the outcome could be. And what we observe is that the bound that you obtain is pretty close to the perfect bound that one can achieve. So the shown in here in red and green are the previous method, and the dashed line is the perfect bound that you can have, and our bound is very, very close to this perfect bound. And we hope that this will be useful for satellite QKD as well, where you observe a large deviation from your observation and a guess. And I guess maybe the last part wasn't so clear, but I apologize. And if anyone wants to discuss with me, you can contact me via email. And this is the QR code for the paper. And thank you.
Thank you, Vaishak, for the very nice presentation. Are there some questions from the audience? Someone can ask for one or two questions.
Sir,
Yeah.
please move to fifth slide, maybe fifth slide.
Hi.
Just sir, fifth. Oh, you can open. I will tell you. Just open. I will tell you.
Yeah.
Further, next slide. Next.
You can see my screen, right?
Where,
Yeah,
sir,
yeah.
where you explain upper tail bound, lower tail bound.
You mean this one or
Upper
this
tail
one?
bound or lower tail bound. Where you explain upper tail bound, lower tail bound, 4 equations were there.
Okay.
Sir,
Do you remember the slide number?
Fifth, sixth, maybe slide something there. Fifth slide, 5.
5. Okay.
5.
Yeah.
August 6. Move to 6.
Okay.
7. No, sir, where you explain upper tail bound, lower tail bound, and inverse, like something where you are explaining that. I have a question from this guy.
Is it here? Like I'm not sure. It's not very clear to
Sir,
me.
it's from start
The
basically.
audio is not.
It's from start where you explain that Chernev type bound for binomial distribution. Yes, yeah, that's.
Is it here?
No sir.
Okay.
First पीछे सर वो गुजर गई पीछे और we did not find. I don't. Okay, thank you, sir.
Maybe you can ask later or connect with Vaishak.
Yes, sir, I will.
email.
Okay,
Yeah.
thank you.
I'm sorry. So, okay.
Okay.
Thank you, Vaishak. Thank you again. And okay, let's
Thank you.
move.
Thank you, Chitra. Thank you.
Oh, no worries. That's fine. So, okay, let's move to our next speaker, who is, okay. So, our next speaker is Dr. Arindam Datta from Society for Electronic Transactions and Security, SETS. Dr. Arindam, are you there?
Yes, I'm there.
Yeah, please share your screen.
Okay, just.
Why me?
Okay, is it visible now?
Yes. Yes.
And am I audible perfectly?
Yes.
Okay.
Please
So,
make it the full screen. Yeah. Okay.
okay. Now is it fine?
Yeah. Yes. Please go ahead.
Okay, so good evening to all, and thanks to give me the opportunity to present or to give a talk in this conference. So my topic is enabling phase matching measurement device independent quantum key distribution via satellite quantum communication. So this talk is based on this paper, which was published in the last year. The work focuses on measurement device independent phase matching measurement device independent protocol, which was previously proposed by Lukenas group, and we calculate with a specific condition, with a specific realistic noise. We consider the realistic noises, and we calculate analytically the security key rate, and then we analyze the result in a LEO satellite scenario using the elliptic beam approximation. That will be the main topic of my today's talk. So quantum key distribution, actually the key distribution is basically this is the process how we can distribute some key, and this key should be secure. Now in classical key distribution, the key is conditionally secure because this is based on the mathematical complexity, and if you have enough good quantum algorithm or suitable quantum algorithm and quantum registers and scalable quantum computer, then you can break with a certain time this any kind of classical mathematical complexity problem. But at the present society or the present security system uses the classical security because of the assumption is that to break the security, if you have the enough computing power, and then you need to have a much more time to break this security. But the reliable time to use the secure key is very less. So this is the conditionally secure. This key is actually conditionally secure, and if you have the quantum computer, then this key may be vulnerable if you have enough resources, quantum resources. So that's why people goes to use the attributes of basics, fundamental attributes of quantum mechanics, and proposed the quantum key distribution. This the first ever proposed quantum key distribution by Bennett and Brassard in 1984. That is the basic structure of quantum key distribution. First, the legitimate parties authenticate to each other, and if the authentication is done, then the quantum key distribution happen, or the once the protocol is done, the shifting part also be done. Then you the legitimate parties got the distributed key, and then to secure if you have the secured key, then you have to perform the privacy amplification and error correction to get the final key, and this shifted key will be reduced to the final key, and that key will be more secure. And if you assume some kind of attacks, this can be the individual attack or the collective attacks by Eve or adversary or coherent attack. This is the most powerful attack. And according to the attack, if you do the privacy amplification, the mutual information with Eve or adversary will be reduced using the privacy amplification, and then you got the final key, and you can use the key with any kind of secure communication. Okay, so this is the basic types of quantum key distribution. Now, one is discrete variable protocol, and discrete variable protocols have also the two types. This is the prepare and measure protocol, like BB84 protocol, B92 protocol, 6-state protocol, and entangle based protocol. This is the popular protocol is E921 protocol. This was proposed by Eckert, and this is basically a device independent protocol. But in discrete variable protocol, when we consider the prepare and measure protocol, this protocol has a flaw, because to perform a discrete variable protocol, you need to have a single photon source, or because this discrete variable protocol demands single qubit state, and in the present technology, the single qubit state is not available, and people use the weak coherent pulse, and with the lesser value of the intensity. So there is a chance for the PNS attack. This is a photon number splitting attack. And if you use the very less value of the mod alpha squared, the intensity of the laser, to generate the weak coherent pulse, so your communication distance will be reduced. So to circumvent this problem, we will propose continuous variable protocol and distributed phase reference protocol. And this protocol helps us to get the quantum security, but if you can use the weak coherent pulse also, that is not a problem. And this communication length, quantum communication length will be also increased. And another kind of protocol is measurement device independent protocol. If you are confident about the instrument or devices used in Alice and Bob's or Legend Party's lab, but you don't need to rely on the Charlie, or Charlie may be the eavesdropper or adversary, and you don't have to rely on Charlie's instruments or any kind of experimental things. So you should use the measurement device independent protocol. But to implement this MDI protocol, you have to have a sophisticated experimental setup. And this is also a variant of twin field QKD. This is also a variant of the measurement device independent protocol, but our focus today is the measurement device independent protocol, specifically the phase matching protocol. And now I just briefly elaborate that MDI protocol with the satellite based scenario. The basic protocols of the PMMDI QKD protocol is Alice and Bob randomly generate a bit values, something Ka and Kb respectively, with belongs to 0 and 1. This is simply, we can say that Alice and Bob randomly generate some sequence with 0 and 1 uniformly, and they use the coherent state. This coherent state is not the phase randomized coherent state. That is, they already selected some kind of predefined intensity, and Alice and Bob use the beat values and prepare the coherent state and send these coherent states to Charlie. This is a third party. Charlie can be eavesdropper also, and Charlie conduct a joint measurement. This is using some interferometer, and Charlie gets some outcome which announced by some plus minus question mark on D. And this plus and minus is represented with the detectors of Charlie's ends interferometer. And plus and minus, when Charlie announces the plus and minus, this will helps to generate the key actually. And these last two outcomes or the announcement will helps to do the parameter estimation part. And this is our quantum channel description. This Alice uses the fiber channel to send her state to Charlie. Suppose this is the Alice's lab and this is the Charlie's lab. This is the Bob's lab. Bob is in satellite station. So Charlie uses the fiber channel to send her states to Charlie, and Bob uses the satellite link. It is more advantageous for Alice to be inside in city and Charlie outside, as this configuration fully utilizes the fiber-based network and minimizes the additional light pollution, because Charlie will be in outside of the city, and the scattering at the receiver end also. And we calculate the security with the loss only fiber and the noisy scenario. This is a realistic imperfection. Loss only means we only consider the fiber has the loss. This is kind of eta like that. And this is a realistic imperfection includes the considering the dark counts of detector, mode mismatch, phase mismatch, detector inefficiency, error correction efficiency, etc. So this is to visualize clearly for a satellite LEO satellite scenario. This L bar is represented by the represented as altitude of the satellite, and the H bar is the thickness of the atmosphere, and L is the link length between the satellite and ground station, and H is the length of the propagation of light inside the atmosphere, that is, and phi is the zenith angle. So, and we also consider the uplink and downlink configuration both for our analysis. So these are the basic equations that we used from the Vogel paper. This is the eta expression, and rho is the position vector within the transverse plane, and U with variable rho and L. This is the beam envelope at the receiver plane at the distance L from the transmitter, and V, this is a very important parameter, and which includes the 5 variables. This x0 and y0 represented the beam centroid coordinates, which is actually this is the elliptic beam, and the x0 and y0 is the beam centroid, and W1 and W2 is the principal semi-axis of the electric beam profile, and phi is the orientation angle of the electric beam. That phi is not the same as the zenith angle. Okay, so this is a transmittance equation of the electric beam approximation. Okay, and there is the some certain value of A1, A2, and A3. You can see in our paper also. Okay, that part was for satellite communication with the assumption of the electric beam approximation. And these are the important equation for calculating the secret key rate. And this omega represented the POVM, which is using by Eve. This is for the there are the 4 POVMs. One is for the detector 1, this is for the detector 2, and that is for suppose no detector is clicked, and omega D is for both detector clicks simultaneously. And this is the POVM equation, and we use the here the 0 represent physically or intuitionally is there is no detection, there is some possibility also. And we use the 2-mode coherent state here. That is the initial coherent state. This is alpha and alpha B, and the beta A, beta B. And after considering the mode mismatch and the phase mismatch, we have calculated the alpha final and beta final. Okay, that is there is total 4 mode actually, because when your mode mismatch is considering, then your 2 mode should be considered at the final stage at the 4 mode, because there is a 2 mode orientation. That is alpha. This is not this is the unchanged mode, and this is the changed mode. Okay. Next. Okay. Okay. That part. Just I want to emphasize that this POVM is not the final POVM, because there is just we only consider the mode mismatch part, and that is the final state or the output state. That is considered by the mode mismatch and the phase mismatch. Then we have to consider, we have to calculate the matrix form of the POVMs, and to get the matrix form, we can use this equation. And after doing some calculation, we will get the matrix form of the E gamma mismatch. And using this E gamma mismatch, we have to consider the detector dot counts, and then we get the final POVM of Eve's instrument of Eve's measurement actually. Okay, so this is the expression. This is the final expression for the asymptotic key rate, and in the asymptotic key rate there is some probability and there is some key rate, and this key rate comes from this equation, and this equation involves that involves from the error correction or inefficiency of error correction, these delta terms. And this chi is the hollow bound or hollow information, you can say that. And to calculate the hollow equation, we use this table, and using this table, these states are represented as the B basis in our work, the B basis elements actually in our work. And this table helps us to calculate the conditional probability, which helps to get the hollow bound. And to get the hollow bound, there are 2 things is needed. One thing is conditional entropy, and one thing is the corresponding density matrices or density operators. And this will come from this B basis elements. This is the plus root over mu, plus root over mu, minus root over mu, something like that. You can see the whole calculation in appendices in our work. So after calculating the key rate and getting the transmittance value, we plot the results with the transmittance and the initial beam width. If we increase the initial beam width this is in centimeter, then the transmittance will be increased. That is expected. Then we perform to get the probability distribution of the average key rate. And this figure A is correspond with the loss only scenario, or B correspond to the noisy case scenario. And both of the scenario, we can observe that if we suppose in loss only scenario, if we go with the less amount of zenith angle, and less amount of or less value of the fiber length, the key rate, the average key rate is more. Hello.
Sorry,
Yes.
Dr. Arindam, we have
Yes.
left with only 1 minute or two, so could you please also wrap up
Okay,
soon?
okay,
Yeah.
that's fine. So, we can see that if the zenith angle and the fiber length is lesser, then the key rate is more, average key rate is more, and the probability distribution is also more, but the value of the probability is lesser. But if you go for the greater amount of the zenith angle or greater value of the fiber length, the average key rate is lesser, but the probability, the value of the probability is higher. Okay, and we use the 1550 nanometer uh, laser, and this is the advantage of the 1550 nanometer. I just skip this part. Okay, and this is the average key rate plot, and we use the we use the six conditions, 6 different conditions. There's 3 day condition, 3 night condition. In day conditions there is no wind, moderate wind, and the windy conditions. And in night, these are clear, slightly foggy, and the moderate foggy conditions. And we can see that in the day 1 condition, the key rate is higher, and the highest, there is the highest key rate. And for the night time 3 condition, that is the moderate foggy condition, that is the lowest key rate condition. And the plot A and C is similar or same plot actually. This is just in the logarithm graph. And in the logarithm graph, we can see that in some conditions, some day or night conditions, we get the higher value of the key rate, and when the key rate is negligible or tends to 0, the fiber length and the free space length is also more, and these conditions is the day time condition 2. And similar thing is happening in the noisy scenario, and there is daytime condition is the more effective, or there is these conditions covering more length of free space as well as the fiber length. Okay, thank you. Any questions?
Thank you, Dr. Arindam. Are there some questions from the audience? In chat, there is some. Okay, can you see, Arindam, how does this model integrate into MDI QKD protocols?
Because first of all, you have to calculate the key rate equation for the MDI QKD protocol, and there is certain well-defined equation to calculate the average key rate. You have to incorporate this key rate equation, and in your key rate equation there is some part which is the variable of the transmittance, and you have to replace the transmittance with the transmittance value of transmission expression of elliptic beam approximation, and then you can get the average key rate for the MDI QKD with the assumption of the LEO satellite communication. Okay, so in your key rate equation, there is a variable which is called the transmittance. You just need to replace the transmittance with the transmittance of the satellite based transmitters. That is, you can go through also our paper, that you can clearly get the idea.
Okay, thank you. Are there any more questions? If not, then maybe we can. Okay, so thank you very much, Dr. Datta, for the very nice presentation and the work as well. Okay, so let's invite our next speaker. She is Dr. Neha Patania from IIT Roorkee. Dr. Neha, are you there? Yeah, okay.
Hello, ma'am.
Hello, yeah. Please share your presentation.
Is it visible?
Yes.
Make it full screen. It's not full screen.
Yeah.
So, hello everyone. So, firstly, I would like to thank Pathak sir, Sandeep sir, and Shivani ma'am for organizing this conference and giving me the opportunity to present my work here. So, today I will be talking about finite key analysis of Cow QKD protocol. So before we go into or talk about the cow protocol in detail, let us first talk about that why do we need to do finite key analysis, like what are its advantages over asymptotic analysis. So in asymptotic regime, we assume our data to be of like infinite data length, n approaches to infinity. So what happens is that in that scenario, the statistical fluctuations, they average out perfectly, and which often results in the overestimation of the secured key rate for real devices. Now, in the finite key regime, it deals with limited data blocks, for example, of the size n equals to 10 raised to power 8 bits, and it ensures security even with a very limited number of exchange signals. It also explicitly bounds the statistical uncertainties epsilon, which are required for composable security in practice. They also provide confidence levels for parameters like QBER and phase error rate. It deals with fluctuations due to finite sampling, and because our real-world QKD systems, they operate with finite data, therefore, it basically requires, there is a need to like explore these rigorous security bounds. Okay, so this COW basically stands for Coherent One-Way QKD Protocol. Coherent because coherence is needed for the security check. One-way because basically there is LS sends the signals to BOP, and the transmission of signal is just one way only. So as you can see in the figure, so we have like LSS setup and BOP setup. So what happens is that these COW QKD protocols, so they falls under the category of DPR class of protocols, which is distributed phase reference kind of protocols. So they are a kind of like prepare and measure protocols, and they also like uses weak coherent pulses. So here the signals are not like sent as a single photon signals, but LS basically sends the signals as pair of pulses. Now what happens is that on BOP side, you can see that there is a beam splitter. So it actually divides the incoming pulses into data line and the monitoring line. Now these data line and monitoring line, they are actually serving two different purposes. So data line is used for key generation, and the monitoring line is used for security check. Now the phase difference between two successive pulses here remains consistent, which is 5. Okay, so yeah, so information, as I said, that this is encoded in the time of arrival. So suppose we are considering two time bins, T0 and T1. So if we have like a coherent pulse in the first time bin and a vacuum in the second time bin, then we call it bit 0. If we have a vacuum pulse in the first time bin and a coherent pulse in the second time bin, we encode it as bit 1. And for security check, we sometimes send like decoy state. So if we have like both the coherent pulses in the time bins T0 and T1, so that makes it a decoy state. And security is basically based on maintaining coherence between these successive pulses. Now, the advantages of COW using COW QKD protocol is that they have like simple hardware, and they are also telecom friendly. We are using normal lab grade fiber here. Okay. So next we will talk about the 2 decoy state variant, which is provided in the Lee et al. Paper in 2024. So the original COW QKD protocol that we have just talked about, so that is susceptible to zero error attacks. Now, these zero error attacks are the kind of attacks where Eve intercept all the pulses and it resends only when it is very sure about the bit value that it is correct. And this potentially introduce zero errors on the data line. So Eve here uses basically USD, which is called unambiguous quantum state discrimination method on LSS signals. So what we can do is that we can insert extra vacuum pulses by which Eve cannot distinguish these sequences without disturbing the coherence. And any measurement attempt will break the phase relationship between these decoy pulses. And that will, the result will be that the Eve's presence will be immediately visible on the monitoring line. So here you can see that with the decoy state alpha alpha, we are also sending a vacuum decoy pulse, which is 0 0. But there are some challenges which are involved in the finite key analysis of COW protocol. So this TPR protocol, like the COW protocol, they are not using basis choices as we have in BB84, which makes the parameter estimation harder. Also, these decoy state methods, they are quite difficult to implement, limiting the ability to tightly bound the photon number statistics. Also, because the finite size effects, they introduce fluctuations in estimated quantities, like in the phase error rate. And this phase error rate calculation, this is very crucial for privacy amplification, but it is not directly observable in COW protocol. And it must be inferred through modeling, that is by calculating bounds on the overlap of signal states, which we will discuss in the coming slides. Okay. So this is the finite key rate formula. So this formula basically represents the lower bound on the finite key length. So this depends upon all these parameters. We will discuss them one by one. So NZ is basically the total number of clicks which are observed on the data line. EP bar is the upper bound on the phase error rate. And HX is basically the Shannon entropy. So we will calculate H of EP bar. And leak EC is basically error correction. So after the error correction, so some bits are like exposed. So the error correction leakage, it is expressed as F dot NZ H of EZ, where the correction efficiency F is considered to be 1.1. Epsilon correct, it represents the correctness parameter. So basically it tells us that the probability that Alice's and Bob's keys, they do not match. They must be of the order of 10 raised to power minus 15. And epsilon secret, it represents the secrecy parameters. And this also tells us that the probability that the key state is not perfectly secret is of the order of 10 raised to power minus 10. Okay, so for finite key analysis, we need to do a security proof, and which is very important because we have to show the security against some of the powerful attacks. So without a security proof, one cannot be sure whether the key that has been generated can be safely used for the communication task or not. So here we are using a virtual entanglement-based protocol, which is provided in this paper by Lee et al. Now, what they are doing is that they are showing the security against coherent attacks. Now, coherent attacks are like the most powerful class of quantum attacks. Because in coherent attacks, what Eve can do is that she can store all the signals that Alice was transmitting to Bob and in her quantum memory, and she can like store it for a later time. Like she can do a measurement later on. Okay, so these are like actually considered the most powerful kind of attacks. So here they have used a virtual entanglement-based protocol, which is equivalent to the actual prepare and measure protocol to obtain the secured key rate in the finite key regime. So what is happening is that Alice, she's preparing some k pairs of the entangled state and randomly measuring the ancillary qubits in either the Z or the X basis. So what happens is that if she measures in the Z basis, she will get a raw key string Z data, and if she measures in the X basis, she will get a raw string X8 delta, and the corresponding optical modes, they are then sent to Bob. Following the approach of the practical COW-QKD protocol, Bob will then detect the incoming optical modes randomly either on the data line or on the monitoring line. So what happens is that if the detector DT, if it clicks at the earlier moment T0, then Bob will record it as a bit value 0. If it clicks at a later moment T1, he will record it at a bit value 1. So this will form Bob's raw key ZB delta. On the monitoring line, the raw key XB delta is obtained. So there is a click on the detector DM0. So that denotes a bit value 0. If there is a click on DM1, it will denote a bit value 1. So for a secure protocol, we require that the probability of these two bit strings, which means that the raw bit string of Alice and the raw bit string of Bob, them not being identical, it should not exceed a predetermined value, which is epsilon correct, and this is of the order of 10 raised to power minus 15. Also, we say that the protocol is epsilon secret if the trace distance between the actual joint quantum state rho AE and the ideal state rho AE, it does not exceed a predefined value delta. And a protocol is epsilon is secured if both epsilon correct and epsilon secret, they will be less than equal to epsilon s. Okay, So next, we calculate the bit error rate on the data line, which is defined as EZ. So now here what happens is that suppose if I'm considering G0Z T0, so basically this defines this 0Z, consider it to be like there is a pulse like alpha in the first time bin and there is a vacuum in the second time bin, which is T1. So which means that you should only get a click in the first time bin and no click in the second time bin. And similarly, when we have G1Z T0 or T1, so there will be basically a vacuum in the first time bin, so there will be no click, and there will be a pulse in the coherent pulse in the second time bin T1, which means that we are going to get a click there. But there can be like false click due to number of reasons, maybe because of dark count rate probabilities and also therefore there is the errors which are arising, they are represented in the numerator and the total gain is presented in the denominator. So this is what I have just written here. Next, we will calculate the phase error rate. So this phase error rate EP bar, it is defined as NP bar by NZ. Now this NP bar is basically the upper bound on the observed value, which we are basically calculating the clicks on all the detectors. And NZ is the experimental value, which is the click count on the data line. This parameter NP bar, it is not easier to calculate. So this is basically a bound. We calculate it using Kato's inequality, which has been recently proposed as a method to provide tighter bounds. This technique, it strengthens the security against coherent attacks and also enables us to achieve a higher key rate. Also, the essence of finite key analysis is to obtain the theoretical bounds on the security parameters like phase error rate and then use the mathematical tools to account for the statistical fluctuations in the obtained data to get the key rates under practical conditions. Okay. So next we will talk about that how we are going to calculate the gains on the data line and on the monitoring line. So the gains are basically given by this equation where these KIs, these are the Gauss operators corresponding to the detected DMI. Now, because here we are considering realistic conditions, so to model the realistic condition, we consider the role of the detector as an amplitude damping channel, which captures the loss mechanism during detection. And for these kind of scenarios, we have a single photon detectors here. So to calculate the click probability or gain, the Gauss operators, they becomes 1 minus 0, 0 for at least one photon click, and K1 equals to 0, 0 for no photon click. I will just explain this diagram a bit to see how these gains are basically calculated. So this is, suppose this is a schematic diagram of the Gauss QKD. So you see that we have a 90:10 beam splitter here, which means that 90% of the pulses, incoming pulses, are going to the data line and 10% will be fed into the monitoring line. In the monitoring line, we have a MZI setup, which actually is a 1-bit delay MZI setup. Now, what is happening is that a beam splitter actually it has like 2 input and 2 output modes. So 1 and 2 are the input modes, and 3 and 4 are the output modes. So as we have like the incoming pulses coming through one mode from one of the modes only. So the other mode, we consider it to be a vacuum mode. And by using a displacement operator, which is exponential of like alpha a cap dagger minus alpha star a cap, so which uses your creation and annihilation operator. So by using this, we calculate these output states 3 and 4. Now the output state 3, this will be used to calculate the data line gains, and the state 4, it will again be fed as an incoming state to this beam splitter. Now this is a 50-50 beam splitter, and this phase shifter, this introduces a phase pi by 2 here, and we will get the outputs DM0 at DM0 and DM1, which are used to calculate the gains for the monitoring line. Okay, so these are the data line and the monitoring line gains. So here, but one thing that we have to specifically remember is that if we are calculating, suppose gain of the detected DM0, so we have to take the probability that we are getting a click at the detected DM0 But we also have to take into account the probabilities that we will not get a click at the detected DM1 and also at the detected DT. So these things will also be incorporated while or taken care of while calculating these gains. So PD here is the dark count rate probability, mu is the mean photon number, and eta is the total transmission loss, which is given as eta d 10 raised to power minus 0.02 L. L is the length of the fiber. TB is the beam splitter transmittance. So here we are like considering a asymmetric beam splitter. So this is basically 0.9 TB. The value of TB is 0.9.
Sorry to interrupt, Dr. Neha. So it's now time for the questions. So please, could you wrap up soon?
So these are just the experimental parameters that we have considered, and these are the results. So this is the Kuber versus fiber distance. So we can see that if I have considered when the detector efficiency is 10%, then the protocol is secure up to a distance of 156 kilometers approximately. And when we are considering the detector efficiency to be 20%, then it is secure up to a distance of 170 kilometers. So we are considering the threshold to be 5% here. So above 5%, the protocol is considered to be insecure. Okay, and these are the results for phase error rate. We see that they are like increasing monotonically with respect to fiber distance L. So this is calculated by using Kato's inequality. So we need to do optimizations on the number of clicks that we are getting on the detectors. Okay, and these are the secured key rate versus fiber distance. So you can see that here from a distance like 20 to 40, we will see that there is the key rate basically is of the order of 1 kbps. And then it gets like breakdown is happening at a distance of approximately 80 kilometers. And for when the detector efficiency is 20%, then we will see that this cutoff breakdown is happening around 90 kilometers. Okay, in the summary, so this finite key analysis framework for cow-QKD that we have provided. Now, this framework incorporates the coherence measurements and correlated detection events, which enables accurate parameter estimation for secure key generation. And an experimental realization of cow-QKD is demonstrated, and its performance is analyzed under realistic conditions like Kuber, PER, key rate. And the secured key rate, it strongly depends upon system parameters such as detector efficiency, fiber loss, attenuation, and detector dead time. We have also been able to show that the cow-QKD system, it can be considered to be secure over the distance in the range of 150 kilometer if we use normal telecom grade optical fiber and SPAT. And the distance for secure key generation, it can be increased to 273 kilometer if we use ultra low loss optical fiber and highly efficient SNSPTs. So this is the paper that you can see for reference. So this is finite key analysis of experimentally realized practical cow-QKD protocol. And thank you.
Thank you. Thank you very much, Dr. Neha, for the very nice work and presentation. Are there some questions? Anyone has some questions? One or two? No, I think. Okay, so if there are no questions, so let us thank Dr. Neha for very nice work. And we move to our next speaker, Dr. Okay, so he's from the Center for Quantum Science and Technologies, IIT Mandi, Mr. Apur. Mr. Apur, are you there?
Yes, I'm here. Am I audible?
Okay. Yes, you're audible and you can share the screen, please.
Okay, thank you. Is my screen visible now?
Yeah, yes. Go ahead. It's perfect.
Yes. So I'm Apurv and I'll be presenting a topic, efficient circuit compression using multi-level entangling gates and linear optical quantum computation, although it's not related to QKD. It will be majorly related to quantum computing. So in this era, the quantum computers are limited by many factors like decoherence, majorly decoherence, and the errors accumulate with the depth of a circuit. Quantum circuit compression is the field that deals with reducing the number of qubit gates to implement a given unit tree. So I'm going to talk about a very specific problem that plagues this field, and then I'll discuss a possible solution to it for gate-based linear optical quantum computation. So in that particular form of quantum computing, we encode the qubits using single photons across two spatial modes. It's called dual rail encoding. This little schematic here shows a scenario in which one qubit represented by this red wire labeled Q0 is represented by two modes, optical modes labeled 0 and 1. And this adjacent figure shows a quantum circuit that consists of, it's a typical quantum circuit consisting of many 1 qubit and 2 qubit gates. So when it comes to linear optical implementation of these gates, single qubit gates can just be implemented using beam splitters and phase shifters, and these implementations are completely deterministic, given that the photon isn't lost. But two qubit gates aren't so lucky. Since two photons do not interact, we must rely on non-linearities, which are very inefficient. So at the start of the 21st century, measurements were used to introduce some non-linearities and simulate photon-photon entanglement by post-selecting desired outcomes. But that comes at a cost. The two qubit gates are no longer deterministic and succeed with a typical probability of 1 by 16, between 1 by 16 and 1 by 9. And this is one particular schematic of a gate that was given by Nil, Laflamme, and Milberg in 2001. It has a success probability of 1 by 16, although the gates of this class succeed with a maximum probability of 1 by 9 that I have written here. So for a circuit that contains n such gates, the probability of success falls drastically as 1 by 9 to the power n. So to make this field scalable, we either need to increase the success probability of these gates, which people have been trying since 20 years without any success. Or the other way can be to reduce the number of such gates that are required to maximize the overall success probability of the quantum circuit. So I will discuss one possible way of achieving the latter, that is to reduce the number of such gates. It is termed qubit-to-qubit circuit compression. In contrast to two-dimensional qubits, qubits are d-dimensional quantum systems, and a photonic qubit in spatial encoding can be realized using by allowing a photon to exist d spatial modes as compared to just two for a qubit. So in this compression scheme, we utilize a qubit with 2 to the power n spatial modes to encode n qubits onto it. For example, this little diagram here shows 2 qubit represented by blue wires surrounded by a curly bracket, meaning that these 2 qubits are encoded onto just one single photon, and these purple wires show the optical modes that are assigned to that particular photon. So by calling these labels 0, 1, 2, and 3 for these 4 optical modes and representing them in binary, we can assume that this photon carries a 2-bit information. So we can say that each optical mode represents a joint state of 2 qubits. And we can extend this analogy to conclude that 3 qubits can be represented by 8-dimensional qubit, 4 qubits can be represented by 16-dimensional qubit, and so on, and generally. But why should we care about it? So to see that, let's look at this figure, which again consists of 2 qubits, but we consider here a controlled operation between those 2 qubits, which are encoded onto the same photon. So if we say the leftmost qubit is Q0, which is the control qubit, and the rightmost qubit is Q1, the target qubit, then the controlled operation should be the one that transforms the state 10 to 11. And we see that this is achievable just by a swap of modes. A photon that began in 10 ends up in 11, and vice versa. This is a deterministic 2-qubit controlled operation, which does not require any non-local gate, which is probabilistic. And such a gate can also be converted into a controlled phase gate by just sandwiching that swap between 2 beam splitters, which are nothing but Hadamard gates. So it might seem like we can just keep on increasing the number of optical modes assigned to the photon, and we can simulate n qubit quantum computer, but that is generally not the case because one photon in itself has no quantum phenomena throughout the circuit. It can effectively be simulated using a classical laser pulse. To take advantage of phenomena that are truly quantum and have no classical analog, we require at least 2 photons. So once we have 2 photons, then we are again faced with the challenge to entangle them, which are now qubits and not qubits. So to see one such scenario, let's consider first a 4-qubit circuit, and each qubit is encoded on a separate photon, and this black colored bar and 4 dots represent a control gate, uh, which acts when all the 4 qubits are in state 1. So this control gate applies a pi phase flip when all the qubits are in state 1. But this is even harder because it requires 4 photons to interact. So instead of that, we decompose it into like 5 gates that are on 2 photons, and the success probability of only this operation is 1 by 9 to the power 5, which is diminishingly small. Coming to the scenario when each photon has on itself like 2 qubits, we see this particular scenario and this particular optical implementation. In this particular scenario, this gate would then correspond to applying a phase flip when the first qubit is in 1-1 state and the second qubit is also in 1-1 state. So we just pair this level 1-1 with another level, same for the second qubit, and borrow a 2-qubit gate onto this architecture to realize that circuit in just one operation. So the success probability is 1 by 9 in this case, which is a massive improvement. But it should be noted that these wires are passing straight, not interacting with any other gate. So these carry the tendency to skew the amplitude, and hence corrupts the output state. So we want some gates that are truly native to qubits and not borrowed from the qubit architecture. But still we see that such an operation can be applied with a very good success probability compared to the previous one. But we hit a bottleneck when we have one such scenario in which we want a controlled operation between 2 qubits, which are now encoded on 2 different photons, and they are already encoded in those qubits. Now the gate, now we have seen in this optical implementation that each each level now represents a joint state of 2 qubits. So it is impossible to isolate a level to represent just 1 qubit. So such kind of gates are impossible now because every gate that we perform will have all qubits that are participating. So we need to remove Q0 and Q2, these 2 qubits, from the control. For that, Q1 and Q3 should have a gate that is triggered whenever they are 1, irrespective of the states of Q0 and Q2. So the gate should be applied for all possible combinations of Q0 and Q2. That's why we need 4 gates to implement this particular circuit that could have been just implemented by 1 gate in the traditional encoding. So this effectively nullifies the any advantage given by the circuit compression, and the probability falls to 1 by 9 to the power 4. So to circumvent this, we need 2 things. First is a gate that is native to qubit architecture and does not require us to borrow the gates from qubit architecture. Second is a gate that implements all these 4 operations, which takes multiple levels across one qubit that would trigger the gate, and does not require to be branched into many operations, or needs to be branched into as less operations as possible. We call them multi-level entangling gates, and removing removing R1 and R2 qubits in general from as control from 2 qubits requires 2 to the power R1 plus R2 operations in a standard encoding. We want to do better than this. That's what's going to be our aim. So now we discuss possible implementation of that particular multi-level entangling gate. So to motivate a generalization, I start with 2 qubits, which are both 4-dimensional, and we assume that we have complete knowledge of their states, psi prime and psi double prime. We we identify few trigger modes across these two qubits. Say 2 and 3 are the trigger modes in the first qubit, and 1 and 3 are the trigger modes in two qubits. So whenever the two qubits is in a joint state of any four of combinations of these trigger modes, then a pi phase flip would be applied to the joint state of the qubit. This effectively means removing qubits Q1 and Q3 from control across the two qubits. So once we have identified the trigger modes, we introduce some ancilla modes to facilitate the entanglement generation. And those ancilla are such that they have the number of optical modes that are one more in number as compared to the number of trigger modes in the input qubit that it is going to be paired with. So first qubit has two green colored wires which represent the trigger modes. So the ancilla will have 3 spatial modes, and the same for the second qubit. Once we have that, and we already assume that we know the initial state psi prime and psi double prime, then we know the coefficients of these trigger modes, and we know the state of these green wires. We use exactly those that particular state of this green wire, and then take a balanced superposition of the state of those green wires with the remaining state of the blue wire. So that would be chi c plus ket 2 by root 2. So that's a balanced superposition of the green modes and the blue mode. So once we have prepared the ancilla states, we want to pair the input and ancilla as we do by this. So what we do is we perform a partial swap or the routing of only the green modes that correspond to the trigger modes. So let's see how it actually helps us. So we just take the first pair, which was in state psi prime and phi prime, and see what happens to the 4 cases of the photon inputs that are possible. So first possibility is that both the photon are in these blue wires that correspond to non-trigger states. The other possibility are both the photons are in green wires, and the other possibilities are green-blue and blue-green respectively. What happens to these photons? So these blue ones pass untouched and they are as they were, and these green ones, they cross over to the other side, and again we have one photon in the input qubit and in the ancilla. But in these scenarios, the other scenarios, both the photons leak into either the ancilla qubit or the input qubit. These are the scenarios we will look to reject, and we will only accept the scenario when we have one photon per system. So when we have that, we have kind of an entangled system of input and ancilla that tells us that when the ancilla is in blue wire, the input qubit is also in the blue wire, and when the ancilla is in green wire, the input qubit is also in green wire. So this is in this way, the ancilla carries a 2-level information whether the qubit, input qubit, is in trigger state or non-trigger state. Coming back, so since we know that the ancilla carries only 2-bit information, we don't need 3 wires for it. We perform a basis rotation such that the ancilla is now just a 2-level qubit, and then we have a resource state which can be read as whenever the ancilla is in state 0, that is the blue wire, then the first qubit, input qubit, is in state M, which does not belong to the trigger mode. And similarly, when the ancilla is green, that is state 1, then the input qubit is in a state M, which does belong to the trigger mode. So we have such a resource state. So now that is also the case for the second pair. Now we apply a Hadamard to impart a phase, and then we perform the Bell state measurement on the joint state of 2 ancilla. So what it does is it basically swaps the entanglement, and earlier we had first pair and second pair of entangled states. Now we project the ancilla into an entangled state, so we have swapped the entanglement, and now we'll have an entangled state of psi prime and psi double prime. To see what we have achieved, let's look at this initial state that we had as an input, which has 16 terms in the superposition. Final state can be seen to have a negative sign only when the joint state of the 2 qubits is a combination of the trigger states like 2-1, 2-3, 3-1, and 3-3, which were in fact chosen as the trigger states, and that was the desired action that we wanted. writing it in logical encoding, we see that these are the 4 states in the logical encoding. Here, the qubit 0 and qubit 3 are 1, 1 in all the states. And we take all the possible combinations of like the other 2 qubits. Effectively, we have implemented a phase to the qubit 0 and qubit 3, irrespective of the states of the other qubits. Now, there is a caveat, by the way, because we started with the initial information of the qubit, which is the luxury that we don't have when we are performing quantum gates. And we needed the input information because we prepared the ancilla in a particular way. We crossed
Sorry to interrupt, Mr. Apurva, could you please summarize soon because
yes.
now the time is up.
Yeah.
Yes. Yeah.
I'll take two more minutes, please.
Yeah. Okay.
Yeah. So we see that when we have only one trigger state, ancilla preparation is trivial, and the scheme becomes completely state independent for 2 levels, but we want a multi-level action. So inspired from this, what we already wanted was to generate a resource state. So we take inspiration and use the 2-level state independent gate to kind of generate a resource state by like pairing up the trigger states with the ancilla. So we apply 2 such state independent gates sandwiched between 2 Hadamard so that the control phase gate become the control NOT gate. And this again lets us make a resource state, and we do the same for the second pair as well, and then proceed similarly performing well state measurement. Now what it does for us is it helps us produce multi-level entangling operation in only 2 to power R1 plus 2 to power R2 operations, which is exponentially better than the standard approach where both R1 and R2 were raised as the power of 2. So this approach can then be generalized for the state-dependent scheme, which has d dimensions, and also ancilla is k1 dimensional. What it does for us is, now I'll just summarize what like advantages we get from that. So this generalized state-dependent approach can be used to generate any form of entangled state of any number of qubits encoded on 2 qubits at a probability of 1/8 that does not scale with dimensions. Such a scheme may be extremely useful for variational quantum algorithms utilizing qubit-to-qubit compression schemes on a NISQ hardware. In such schemes, we generally begin with a non-input state, and this scheme can easily be deployed to generate entangled state of any number of qubits at a fixed cost. Same generalization we can do for the state-independent approach as well. And again, as I mentioned earlier, it can be used to remove R1 and R2 number of qubits from 2 qubits as controlled by only using this many number of operations as compared to 2 to power R1 plus R2, which is an exponential improvement. This is the generalized state that we get from the generalized scheme, which in this summation, each term is a joint state of the input qubits, tensor product, the joint state of the ancilla, and we have this the 5 plus Bell state, and we have 4 terms corresponding to the each Bell state. So if the ancilla is measured in the 5 plus Bell state, then our input qubits are in this particular entangled state where the minus sign is accompanied with all the trigger terms. For other measurements of ancilla, we have slightly skewed, so this minus sign is shifted, but these are just poly errors which can be corrected by active feed forward. So this approach can be used to save the circuit compression schemes for the selectivity bottleneck that I discussed. So just to summarize that, qubit to qubit circuit compression schemes provide us a way out of provides us a way to scale the linear optical quantum computing. However, they suffer from a selectivity bottleneck in which you cannot have entanglement easily, and we provide 2 schemes. First schemes work irrespective of the dimensions at a constant success probability, and the second scheme drastically improves the resource requirement as compared to the standard schemes. So this work is currently on arXiv. Thank you.
Okay. Thank you. Thank you very much, Mr. Apur. Are there any quick questions from the audience? Any questions? No questions, I guess. Okay, so thank you very much, Mr. Apur. And now we invite our last speaker of the session, Mr. T.S. Gururaj from Sastra University, Thanjavur, Tamil Nadu. So, okay, so he's already here. So, okay, now you can go ahead. Okay. Okay, Gururaj, you can go ahead. We can't hear you. Are you speaking?
No, ma'am.
Okay. Now we can, yeah. You can start now, please.
Can you able to see my screen, full screen?
Yes.
Is it full screen, ma'am, or?
Yes, I think yes. Yes,
This
yes.
is full screen. Everything is fine. You can start your presentation.
Okay, sir.
But now it's not full screen. You came out of full screen. And this is fine.
Yeah.
Perfect.
Okay. I'm Guru Raja. I'm working as a project assistant in Sastra Deemed University under the guidance of Dr. Padmapriya Praveen Kumar ma'am. I'm going to talk about development of quantum cryptographic algorithm for next generation secure system. I identified some research gap to make a current cryptographic systems, PRNGs, are vulnerable to the quantum based attacks, so that quantum random number generation needs a key as a key role for the encryption. And in quantum image encryption, heart of the encryption algorithm is a key. So the key is a resource. QRNG is needed for that to make a secure more the encryption parameters, and we need a hardware based authentication system also to require hardware security concerns also. And I identify some research gaps to why we need a quantum random number in encryption means probabilistic and unpredictability there, so that we use the QRNG, and QTRNG provides a true random entropy but some lacks in a structural complexity. QPRNG uses a deterministic structure but lacks in a true entropy sources, so that here the proposed method is a QHRNG. This will be combines the true entropy with the circuit complexity, so that we need to integrate our QRNG with QKD to secure transmission through the sender and receiver. In image encryption, we need to use the key as well as whenever the intruder is there in our quantum channel, we can easily detect using the no cloning theorem. And why we need a hardware-based authentication, unauthorized access can be removed, so that we need a hardware-based authentication system also. Quantum is fast computation, highly processing. Why I am choosing IBM Quantum means number of qubit is very high compared to others, and quality of quantum volume and enhances the quality of the states, and circuit layer operating per second is also high. So that our first aim to make a true random entropy for the HRNG sequence. First, I'm going to initialize the quantum state. After that, I apply the superposition layer. This superposition creates a probability of 0 and 1, both that, using the Hadamard gate. After that, creating an entangled layer of CRZ gate. This increases the controlled entanglement and ensures that the stable quantum interference has been there in the quantum system. Here, the true TRNG sequence, finally we get the Bell inequality based states, so that the QTRNG produces here the no repeatability in the there is a no repeatable pattern in the true random sequence. The proposed circuit consists of a Hadamard with the controlled ORZ gate, and the Hadamard is going to produce a superposition. After that, controlled rotation pi by 2 enhances the entangled layer. Finally, if we measure means we get the TRNG outcome. The proposed algorithm consists of, we need a number of qubits, and what rotation we are going, the phase we can able to alter the modulation, phase modulation also there. If we want to make a different QRNG sequence, we need to alter the phase value, we get the different outcomes. And the proposed circuit is sent through the basic simulator as well as AES simulator, the noisy and noiseless simulator. But after the simulator verification, we can go for the real quantum hardware also. In this QPRNG circuit, quantum pseudo-random circuit, here the pseudo-random circuit, what pseudo-random means deterministic, that deterministic sequence we are given in the circuit level itself. So the phase pi by 2 around the z-axis as well as the DCX gate control the bidirectional control logic gate. It enhances the qubit routing and efficient entanglement also in the QPRNG circuit. Finally, this QPRNG circuits also run in the simulator as well as a real quantum hardware. And QHRNG, this HRNG takes a TRNG as a seed sequence to produce a QHRNG. Finally, the TRNG sequence are getting applied using the poly-X gate. Whenever the zero state means zero only, the state is zero only. Whenever it 1 means we need to apply the X gate to flip the 0 to 1. Finally, we apply the TRNG as a sequence. After that, apply the QPRNG circuit. Here, the QPRNG with the QTRNG seed, we get a hybrid random sequence, quantum hybrid random number generation circuit. This is the circuit. Here, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1. This is a seed sequence. Here, this is a PRNG layer. Finally, we get the HRNG sequence, hybrid random number sequence. This test has been sent through the NIST standard test for the NIST 22 for the randomness verification as well as a 90B for the entropy verification. The TRNG achieved a 0.7 entropy and PRNG 6. HRNG is the highest amongst all the test case, 0.71. Entropy is also high. And these tests has been taken a Bell verification test as well as a AAS 31 test as well as a test U01. All the test case also we are taken care. And restart experiment confirms that there is a no repeatable pattern in the generated sequence. TRNG also, PRNG also, you can see that the generated sequence is not repeatable pattern, and HRNG also not repeatable. And here the autocorrelation confirms there is a no bit shift between the positive and negative shifts, as well as the zero state only the bits are arrival. Finally, the hardware based, the proposed quantum circuits are run in a IBM Quantum Torino based hardware. So the hardware based raw bit extraction without any post processing. The QTRNG passes 5 test case, QPRNG passes 6 test case, QHRNG while using the poly as a poly gate to increase this will not increase the bias, this will reduce the bias, so that the HRNG creates only 10 achieves a lot of 10 test case compared to the Saheli et al, Lee et al. The collision test, all entropy test, all test cases are passed, achieve the highest entropy of 0.9 compared to the Kumar et al and Zio et al. They are used their test case with the simulator itself. We are run in the real quantum hardware also. The QTRNG relies on measurement induced randomness, offering the high unpredictability but limited noise resilience only. The QPRNG uses a deterministic quantum gate to generate a complex pattern and provides a fixed initial stage to provide the structural randomness but lacking the true entropy source. QHRNG integrate both approaches to make a entropy fusion technique to get the complexity of the entangled quantum evolution. This hybrid random sequence to get the improved entropy level. Finally, we generated QRNG sequence, 3 different QRNG. We are going to share that QRNG in the QKD protocol. QKD protocol, here the QRNG is taken for and we need to share that QRNG for the receiver end using the basis state. For example, QRNG is going to apply the basis state of K0, rectilinear basis K0, 0 is into the K0 and 1 is into the K1, and X is also diagonal basis and K0 is encoded as a K plus as well as a K minus state. We are going to apply the basis based and apply the Hadamard gate to make a superposition here. Whenever the superposition is collapsed, any intruder is come into the quantum channel, the superposition will be collapsed so that the bits are unlike in the basis. The basis states will be changed. The unlike bits can be removed using the public channel, the basis sharing to the public channel, we are going to remove the unlike basis. Here the proposed method is run through the simulator. The shared key is same in Alice and Bob without any intruder. We are sending the cube through the quantum channel. Here the key exchange using the with eavesdropper. Eavesdropper involves any gate in the middle circuit channel itself. The bit sequence are changed. Here you can see that 0, 1, 1. Here you can Bob will get the other sequence. So we are successfully integrated the QRNG with the BB84 protocol and the secure transmission between the quantum channel with the recalculation and bit shift also taken care, and the experimental validation through IBM quantum simulation over the correctness of the state preparation and measurements as well as a probabilistic outcome. QBER also comparatively very low state also. Then finally, we are going to use our QRNG in the quantum image encryption algorithm. The quantum image, if we take it as an image as a data, we can, if image is working, means we can use any data, the text and video, any form. All the data is going to represent as a, for example, image, we are going to represent as a quantum image as a NEQ, a novel enhanced quantum image representation. After that, we are going, first going to XOR with our QRNG. First layer of encryption is done in the QRNG itself. After that, we are going to apply the NEQR sequence, novel enhanced quantum image representation. After the image representation, the bit level scrambling will be happen using the controlled NOT gate and controlled swap gate. Controlled NOT gate bitwise scrambling in the pixel value itself, and controlled swap gate, the qubit position is changing between it increases the diffusion, quantum diffusion in the bit level scrambling, and we apply the selective QFT. Selective QFT here, the selection of the QFT based on the Hutch and controlled RZ pi by 2. This RX pi by 2 pixel position dependent phase shifts, and we apply the negative phase shift for the decryption itself, and the inverse quantum bit level scrambling also taking the inverse of the encryption algorithm. So the proposed encryption algorithm is run through the QTRNG and QPRNG as well as a QHRNG also. Here the all the keys has been taken. First QTRNG with the A means AER simulator as basic simulator, and again QPRNG with the AER simulator and basic simulator. Finally HRNG with the AER and basic simulator. Finally the QHRNG using the basic simulator, we get the value of 99.5. the entropy, the NPCR value, number of one pixel is changed, means there is a high level of entropy is there, 99.5 level achieved, and the UACA is also the standard limit of 33.4. Here the histogram, the original image shows here the distortion in the image. Finally the encrypted image uniform. If there is a uniform, means there is a no intruder can detect the original image. Finally the entropy, the image is a 8-bit image. We are taken grayscale image 8-bit level. So the proposed method achieve the 7.99 near ideal entropies case also. Statistical analysis also taken, and the correlation, cross correlation, positive correlation and negative correlation also taken, horizontal, diagonal, vertical, all the case, the image is shown the encrypted form, uniform distribution. Pixel is not at all any correlated value, all are in uniform level. The intruder cannot able to take our image, encrypted image back, original image back. We need a heart of the encryption algorithm is a key itself, so that our key achieve a highest level of entropy. Finally the NPCR is also NPCR, UACA, the PSNR must be low, MSE must be high in the image encryption statistics. So all the test cases are high in the HRNG compared to the TRNG and PRNG. The literatures are only using the classical based chaos based encryption parameter. The PRNG also they are taken, but the proposed QRNG implemented on the IBM real quantum hardware and noisy and noiseless simulator also. This proposed entropy, the proposed QTRNG and PRNG achieve the highest entropy, strong resistance to the attack models with the real-time quantum hardware, and polynomial complexity is also there here. The QRNG, PRNG, the QTRNG, PRNG, and HRNG and key-based keying, and this enhances the multi-layer security here and uniform histogram distribution also there, low adjacent pixel correlation, near zero encrypted output, high resistance to the pixel based cryptanalysis also, demonstrated high key sensitivity also, and strong resistance to the statistical attack. Finally, we need a hardware based authentication model to get our key through the dongle based. Finally, we generated a key QTRNG and QPRNG and QHRNG. Finally, these three things is going to generate and send through the cloud itself. Finally, this is as a Sakura Q. It is a product. Finally, this whenever the MAC ID is verified, only the dongle will work. We are going to enter our dongle in our PC. Whenever our dongle and the system level MAC is verified, then only it will be open, otherwise it will not open. The dongle contains encrypted metadata as well as a unique ID also dongle contain. Whenever the ID and encrypted parameters also matched with the system level, then only the GUI will be open. Then the GUI is open means we can enter our password and details. After that, we are going to apply our customer verification. After OTP will be allocated through our mail itself, we can able to enter the OTP, successful verification of OTP, insert the dongle. Then only the dongle opens the TRNG and PRNG, HRNG. We can able to take our quantum key here. This ensures that there is a no brute force attack and finishing attack, MAC based attack, and USB cloning also not possible because MAC ID verified without a dongle. Whenever the dongle contains the metadata as well as a unique ID, then only the correct dongle only work, and that we are going to insert our system level MAC ID also. When the MAC and MAC's verified, then only the dongle going to process all the QRNG process. This QRNG produces a simulator based as well as a real quantum hardware based QRNG also there. The system view is there. Here this is a hardware based system level. This application we are going to use in the banking sector for the high level transaction. Here the client is going to enter their login and password and OTP. Finally, the MAC verified, then only the dongle going to insert. If the dongle matches with the system level, the name and encrypted metadata is clear, then only the cloud-based RNG going to get for the bank system. Whenever the high-level transaction, the crore and million or transaction, they are going to use that QRNG as a key here. They designed a hardware-based authentication model for controlled QRNG access, as well as this has been synchronized with the cloud-based synchronization with the encryption parameters and device binding using the unique ID verification as well as a secure. This firmware validation has been patented for the authentication framework, real-time authentication process, and through the hardware demo also we are seeing. These are all the references.
Okay, thank you. Thank you very much, Mr. Gururaj. It's a very nice work and very wonderful talk you presented. Are there any questions from the audience? Yes, there is something in the chat I can see. Yes, there is a question. Is it possible for a pure unitary quantum system, no measurement, to generate true randomness? Why or why not? Mr. Gururaj? Yeah.
Yes, ma'am. Without measurement, we are not going to get the RNG here. Only state only there. Without measurement, we are not going to get the RNG sequence. Finally, whenever anything we are going to measure, we get the classical RNG only. The unitary gate preserves only norm and information only. The state remains pure state. Evaluation is a deterministic as well as a reversible. When there is a no measurement means not unitary itself. The wave function and there is a no collapse is there. All the superposition will be preserved only. There is a probability of 0 and 1 only here.
Okay.
There is a no collapse, no randomness introduced in the no measurement based.
Thank you. Thank you, Gururaj. Are there further questions?
Sir, please give us general idea about QTRNG, QPRNG. As you explained that we can use as a cryptography like simulation image. You explained that. So I need a general idea about why in practical life why currently we are using that or not like something.
Yes, sir, we can use the QTRNG and QPRNG and QHRNG in many use case. First, QTRNG needed for the true random encoding. That is a true random. We are going to use our, for example, classical AES and RSA encryption. All they are using a classical based PRNG sequence. The classical PRNG is all vulnerable to the seed sequence. For example, if the seed is there in classical PRNG, if the seed is known means we can not able to use that classical PRNG. This proposed QTRNG is uses for the one-time paths. For the perfect secrecy will be there in secure key generation framework. And financial security, the high stack simulations like Monte Carlo simulation, they are going to use our QTRNG. And random sampling in physics-based simulation also, they are going to use our QTRNGs also. QTRNG is information theoretic randomness here. The QPRNG use the seed-based algorithm. For example, high-speed application we need means AML based. We can use our QPRNG as a faster and scalable. And QHRNG, we can use any secure cloud computing and healthcare patient analysis also. We can use our QHRNG models. The
Sir,
QHRNG.
basically,
Yes, sir.
okay, continue, sir. Continue, sir.
Yes, sir. You can tell. No issue.
Sir, basically, I want to just quantum true random generator. Maybe they are generator like something quantum pseudo random generator like quantum hardware random generator QPN, QPRNG, QHRNG, QTRNG like something. So
Yes.
I just want further explanation about like these general idea I just found.
What is the
QPRNG quantum true random generator like something QPRNG quantum pseudo random generator or QHRNG quantum hardware random generator like they stand for
hybrid, sir. Hybrid randomness.
hybrid. Okay, thank you. So I need a general idea about
Okay, sir. All are QRNG itself. All are quantum random number generation. All in the these are all the types. The QTRNG, PRNG, all the QRNG is going to use for our for example OTP send, also high level transaction and any simulation one time pad. All for example we need to use our QRNG for any other purpose also. For example, the high level of seed sequence also we can take this TRNG. TRNG means the repeatability will not be there. If you measure again, you will not get the same sequence again. That is a TRNG, sir, here.
Okay, thank you, sir.
Okay.
Hi, Guraj, I have a question. So, especially when you are looking for the cloud-based scenario, is for the deployment scale purposes, have you also considered or calculated what was the latency? Because that will play important role.
What was the latency?
Yeah.
Yes.
So
cloud-based scenario, there is a latency is also there, sir. Here, network and routing is also there. For example, we are run through the IBM-based hardware only here.
Yeah. So the number,
Through API
do
only.
you have the number?
The latency is only 10 milliseconds, 9 seconds only taken care, sir, here. The generated sequence is 9 seconds.
Yeah, and you can calculate depending on the length of the sequence.
Length is, for example, length depends on the number of qubits and number of shots we are applied. For example, 24 qubits into 1 lakh shots we can able to 24 into 1 lakh. That much times we can. For example, we need to test our NIST standard test. We need a 10 lakh bits. 0 and 1, 10 lakh we need. then only we can go for the NIST standard test.
Okay, so with the 9 second, okay, one can calculate, but I could see, so that should be somewhere in the millisecond, less than millisecond order, right?
Yes. I'm not able to hear you, sir. Currently.
I'm saying that should be less than millisecond order, then fine. It's
Yes.
around millisecond. I'm not sure about that, how to take that shots into account while calculating the latency in this particular scenario. There is some way, but that's fine. Just at least the number is there,
Yes.
so I can calculate.
Okay.
Thank you.
Okay.
I think
Sir, what is pseudo random sequence?
What is pseudo random sequence?
Yes, sir.
The structure itself here, the pseudo random here.
In
PRNG.
QPRNG.
Yes, sir.
No,
Okay.
Param, just don't ask question for asking, for the sake of asking question. The talk was
Okay,
general.
thank you.
I mean, you are again and again asking for general introduction. So
Thank,
something has to be read
thank you, sir.
also. Means, yeah.
Okay.
Pseudo-random numbers are random numbers which are produced by writing a formula, an algorithm, or program. So they are not hardware dependent. They are not dependent on the physical process. Whereas anything where there is a hardware, there is a physical device, those are true random number generated. So when you write something, a program, an algorithm, and generate something, then it's a pseudo-random. So quantum mechanical random numbers are always involve a process, a hardware. So they're in essence true random number generated, but there are classical true random number generated too. So all quantum random number, and it always originates from measurement, because intrinsically there is a postulate called collapse on measurement. At the end of the day, that will be connected to the randomness. So unless you measure, it's not random. And these ideas are very simple, and there are many practical applications. Casinos use random number generator. One can generate OTP through quantum random number generator and share. The difference with the classical things are that classically, if you are just tossing a coin, if you know how much force you have given, it's still there is a physical system. How much is the air drag? What is the gravity? You can eventually find out what will be the outcome. But here the randomness is intrinsically in the collapse on measurement postulate. So hope now read a bit and elaborate on these, and then probably your questions will be cleared in general.
Yes, sir.
The talk was very
Okay,
nice.
thanks.
Means it looks at the practical
Thank you,
applications,
sir.
and I would like to thank not only the last speaker, all the speakers of the day, and both the session chairs from the past session, and as well as the Dr. Chitra Shukla, who chaired the last session. And of course, thanks are due to all the audience who are listening for all these 4 days, so many talks, and probably so many talks, so many new ideas will lead to some more new ideas, some out of box discussion outside that people will find out who with whom to collaborate, who is more interesting to answer. So if something like that happen, next year we see some papers where 2 people are collaborating, or there is a paper is written by 2 people who did not knew before each other before this conference. When they came across this conference, they found that they have something common, and they write a paper and present in the next edition. So something like that happens, then we'll consider that this meeting is successful, and we hope it will be successful, and we hope everybody will join tomorrow also at 6 p.m. for the last day. And tomorrow's first speaker is, I can see him now, but we'll take a break. So Dr. Abhishek Shukla will listen your talk as the first talk tomorrow morning, and your morning, but your afternoon and our evening in India.
Yeah, sure, sir.
So thank you, everyone, and see you all tomorrow at 6 p.m.
Thank you.
Okay, thank you, sir. You are looking very serious today.
Thank you, sir. Thank you.
Let me stop the live streaming.
research.